Imagine a world encased in ice, a world whose scale surpassed even the wildest imagination. Here, in this silent, icy wasteland, the planet itself seemed frozen in anticipation, immersed in a great glacial period when the silence was absolute and stretched for thousands of kilometers. Imagine a landscape so vast, so blindingly white, that the horizon simply dissolved into snowy darkness. In this ringing void, veritable titans, clad in thick fur, roamed. Shaggy giants, mammoths, shook the frozen ground with their mere steps, while deadly saber-toothed cats stalked their prey in the deep snow. The very air was permeated with the echoes of ancient life. It was a story of endless winters, of mysterious wanderings across frozen continents, of incredible creatures that once ruled this land and then vanished without a trace. Today, scientists, digging into permafrost, are discovering giants frozen in time, silent witnesses to that lost era. And while these discoveries provide clues, no one can yet say with certainty what drama truly unfolded here. Even now, as we observe our rapidly changing world, we can't help but wonder about the past. What else lies hidden in the depths of history? What vanished as quietly and imperceptibly as the melting of centuries-old ice? Let's travel back to that harsh yet captivating time, to the very heart of the Ice Age. Get ready for a gripping tale of how the icy shell slowly retreated from the face of our planet. So what exactly is an ice age? It's not just a prolonged winter, but an entire epoch spanning millions of years, when the Earth's climate became significantly harsher than we know it. During these times, vast tracts of land were buried beneath gigantic ice sheets known as glaciers, and we're not talking about small frozen patches. These were colossal, multi-kilometer thick sheets of ice that, like a slow but inexorable force of nature, spread across entire continents. The last such great cold, which is most often referred to when speaking of an ice age, began approximately 110,000 years ago and ended around 12,000 years ago. However, it's important to understand, an ice age is not a one-time event. There was a much longer period in our planet's history when polar ice caps were a constant feature. In a sense, even our time can be considered just a part of this protracted ice age, which began approximately 2 million years ago. It's just that we live in what's called an interglacial period, a relatively warm interval between two phases of great cooling. When most people imagine an ice age, they think of its final, most recent phase in geological memory, which left deep scars on the planet. During that time, the ice sheet reached truly cyclopean proportions, covering significant parts of North America, Europe, and Asia. Let's look at North America. There, the Laurentide ice sheet buried almost all of modern-day Canada and extended its icy fingers deep into the continent, reaching into what are now Illinois and Missouri. And in Europe, the Scandinavian ice sheet covered not only all of Scandinavia, but also the British Isles, as well as parts of modern-day Germany and Poland. Furthermore, the world's greatest mountain ranges, the Alps, the Himalayas, and the Andes, developed their own, smaller, but no less impressive, ice caps. Even lands not directly covered by ice felt its icy breath. Temperatures dropped everywhere, precipitation patterns changed, and sea levels dropped catastrophically. A glacier is essentially a gigantic frozen river of compressed snow, constantly, though almost imperceptibly, moving under the pressure of its own weight. It forms where more snow falls than melts. Year after year, century after century, the snow layers accumulate, compact, and, under tremendous pressure, transform into dense glacial ice. When the mass reaches a critical point, the ice begins to deform and slowly flow, like an incredibly viscous and dense river. Glaciers can fill mountain valleys. They are then called valley glaciers. But what covered the planet during the Ice Age was something entirely different: continental ice sheets. An ice sheet is a massive glacier covering over 50,000 square kilometers. These truly colossal ice caps are so heavy that their own weight causes them to slowly spread outward from their center. Today, only two such giants remain on Earth: the Antarctic and Greenland ice sheets. But during the last ice age, there were several such colossi. Their incredible size and mass allowed them to literally reshape the planet's terrain, pulverizing mountains, gouging out deep valleys, and transporting unimaginable volumes of rock for thousands of kilometers. These icy worlds had a colossal impact on the global climate. Their dazzling white surfaces acted like a giant mirror, reflecting sunlight back into space and thereby further cooling the planet. And the enormous amount of water trapped within them led to a dramatic drop in sea levels. During the last ice age, these giant ice sheets dominated the planet. These weren't just frozen fields, but colossal masses of ice several kilometers thick, whose sheer weight forever altered the contours of the continents. The main players in this icy arena were the Laurentide Shield in North America and the Scandinavian Shield in Europe. Their monstrous might sculpted many modern landscapes. The Laurentide ice sheet, originating in the center of what is now eastern Canada, grew to incredible proportions, covering virtually the entire country and extending far south into what is now the United States. At its peak, its ice edge reached the Ohio and Missouri rivers. Where cities in Minnesota, Wisconsin, Michigan, and New York now stand, a thick, multi-kilometer layer of ice once lay. The thickness of this icy monster in some places, particularly over Hudson Bay, according to conservative estimates, exceeded 3 kilometers. Just imagine a mountain range made entirely of ice, slowly creeping across the Earth, centimeter by centimeter. The weight of this massive mass was so great that it literally pressed down on the Earth's crust, causing the land to sag. And even today, thousands of years after the ice melted, some areas of land once weighed down by it are still slowly rising, as if sighing with relief. This process is known as isostatic rebound, and it is the best evidence of the incredible pressure this land once endured. As it moved, this ice sheet acted like a gigantic abrasive tool, scraping soil and rock from the surface. It tore giant boulders from their bedrock, crushed them into fine powder, and carried them hundreds of kilometers away. This process gave rise to numerous unique landforms, such as drumlins, elongated hills that mark the direction of the glacier's movement, and eskers, long, sinuous ridges formed by rivers that flowed within or beneath the ice. The Great Lakes of North America, for example, are a direct legacy of the erosive force of the Laurentide Shield, which carved out deep basins in their place that later filled with meltwater. In Europe, the Scandinavian ice sheet was no less massive. Originating in the mountains of Scandinavia, it spread far beyond their borders, covering Norway, Sweden, and Finland, and, crossing the Baltic Sea, encroaching on Germany, Poland, and Russia. Furthermore, almost the entire British Isles, with the exception of a few of the highest peaks, were encased in its icy shell. Like its North American counterpart, the Scandinavian Shield reached thousands of meters in thickness in its central sections. Its crushing power carved out the famous Norwegian fjords, deep, narrow sea inlets that were once glacial valleys. As it retreated, the glacier left behind vast plains covered with so-called till, a mixture of clay, sand, gravel, and boulders. These glacial deposits later became the basis for the fertile soils of many agricultural regions of Europe. But the influence of these ice giants wasn't limited to the territories they covered. Their very existence radically altered global weather systems, redirecting winds and ocean currents. Around them stretched vast periglacial zones, realms of permafrost where the ground was frozen deep into the ice, and the landscape was dotted with unique formations such as pingos and patterned soils. The enormous volume of water trapped in these ice sheets caused sea levels to drop by as much as 120 meters. As a result, vast tracts of continental shelf were exposed, and land bridges emerged between continents, such as the famous Bering Land Bridge between Asia and North America, paving the way for great migrations of ancient animals. These icy worlds were dynamic, constantly changing landscapes that left an indelible mark on the face of our planet and forever altered the course of life's evolution. During the Ice Age, the climate of the entire planet was strikingly different from today. The most obvious feature was, of course, a much lower average temperature. Scientists estimate that globally, the planet was approximately 8 to 10 degrees Celsius colder. A difference of just a few degrees doesn't sound all that bad, right? But on a global scale, it was a true climate revolution, with a profound impact on all Earth systems. The climate of the Ice Age was extremely uneven. It was particularly harsh in the high latitudes, near the poles and giant ice sheets, where perpetual cold reigned. However, even in tropical regions, temperatures were noticeably lower than today. Long periods of severe cold alternated with short, slightly warmer intervals, but the overall trend was inexorable. The planet was freezing, and it wasn't just a matter of temperature. Let's travel back to the distant past, to a world bound by ice. But the real battle for survival in those days was waged not so much against the cold itself as against its consequences. A catastrophic shortage of fresh water, constantly changing landscapes, and incredible pressure on the entire ecosystem. It was these harsh conditions that laid the foundation for the development and subsequent triumphal march of modern humans across the planet. It was an era of extreme environmental instability, which, paradoxically, became a powerful stimulus for human innovation and adaptability. We're talking about a period scientists call the last glacial maximum, or LGM for short. It wasn't just a cold period, it was the harshest, most merciless, and longest phase of glaciation during the entire last ice age. This peak of cold occurred between approximately 26,000 and 20,000 years ago. During this time, ice sheets, like white amoebas, expanded to their maximum size, radically reshaping our planet and its climate. To truly understand what life on Earth endured, we need to peer into the very heart of this icy world. Imagine the Northern Hemisphere. It was dominated by gigantic continental ice sheets. In North America, for example, the gigantic Laurentide ice sheet covered virtually all of modern-day Canada and extended its icy tongues deep south into what is now the United States, stopping only at the Ohio and Missouri River valleys. Its thickness was simply unimaginable. Estimates suggest it exceeded 2 kilometers in its central regions, for example, over Hudson Bay. Just imagine, 2 kilometers of solid ice. The weight of this monstrous mass was so great that it literally pressed the Earth's crust hundreds of meters deep, creating colossal deformations on the surface. Incidentally, we still observe this effect today. The Earth, freed from its icy oppression, continues to slowly rise. Meanwhile, the Scandinavian ice sheet reigned supreme in Europe. It covered almost all of Scandinavia, the British Isles, and reached into the heart of Central Europe. But don't think of these ice fields as motionless monoliths. No, they had a life of their own. They flowed under their own colossal weight, crushing rock into dust, transporting enormous volumes of debris and boulders, and carving unique landforms into the planet's surface that we see to this day. Elongated drumlins, sinuous eskers, and even the basins of the Great Lakes. And that's not all. Hidden behind these major ice giants were mountain glaciers. In ranges like the Alps, Himalayas, and Rockies, they also expanded enormously. Now imagine the colossal volume of water frozen and locked in these ice sheets across the planet. This led to a staggering consequence, a sharp drop in global sea levels. At the peak of the last glacial maximum, sea levels dropped by approximately 120 meters, the height of a 40-story building. As a result, vast tracts of continental shelf were exposed, creating entirely new land. Entire land bridges emerged, connecting continents, which became a key factor for the planet's entire biosphere. The most famous of these is Beringia, a wide land bridge linking Asia and North America. It was along this land bridge that the migration routes of ancient animals and, of course, our ancestors ran. Other land corridors also emerged, Sunderland in Southeast Asia and Doggerland, where the waves of the North Sea now lap. All of this dramatically impacted the spread of life across the Earth. Global temperatures during the LGM weren't simply lower. The planet was plunged into a deep, penetrating cold. The average surface temperature on Earth was 8 to 10 degrees Celsius, lower than we're used to today. And this cooling was uneven. It was most noticeable at high latitudes, near the giant ice sheets, but even in the tropics, much cooler conditions prevailed. This bitter cold was further amplified by the high albedo, the reflectivity of the vast ice and snow sheets. The snow-white surface acted like a giant mirror, reflecting a significant portion of sunlight back into space and further cooling the planet. The cold climate also caused profound changes in the plant world. Forests virtually disappeared from the high latitudes and mountain slopes, giving way to vast, treeless expanses. Here, a completely different type of vegetation dominated: tundra and the so-called mammoth steppe. These were highly productive, cold grasslands that stretched across vast swathes of Eurasia and Beringia. These frigid pastures were home to gigantic herds of Ice Age megafauna, woolly mammoths, mighty woolly rhinoceroses, and enormous steppe bison. Harsh periglacial conditions prevailed in the areas adjacent to the ice sheets. Permafrost, permanently frozen ground, predominated, preventing plant roots from penetrating deeply. This led to the formation of unique soil patterns and ice mounds known as pingos. Deserts also significantly expanded their reach during this time due to increased aridity. Atmospheric conditions were just as extreme. Climates around the world became significantly drier as less moisture evaporated from the colder oceans and global air circulation shifted. This led to a sharp decline in precipitation in many regions, causing ancient lakes to dry up and deserts to advance. Fierce, persistent winds were common, driven by the enormous temperature differences between the icy landmasses and the relatively warm oceans. These winds transported colossal quantities of fine sediments known as loess. The winds literally carried fertile silt, which settled for hundreds of kilometers around, creating incredibly rich plains. For example, the famous Loess Plateau in China and the fertile lands of central North America are a direct legacy of these ancient winds. The atmosphere at that time also contained much less greenhouse gases, particularly carbon dioxide and methane. This, in turn, contributed to an even greater drop in temperatures, weakening the greenhouse effect. Direct evidence of this is now available from ice cores extracted from deep within Antarctica and Greenland. In this harsh, unforgiving world, life fought a desperate struggle for survival. Animals adapted as best they could. They grew thick fur, increased in size to better retain heat, and constantly migrated in search of food. Human populations, including early modern humans and our cousins, the Neanderthals, demonstrated remarkable resilience and ingenuity. They developed new technologies, created specialized tools, honed hunting strategies, and built shelters to survive the merciless conditions of the LGM. Humans' ability to adapt to such extreme conditions is a striking testament to their unique adaptability. The last glacial maximum wasn't just a static period of cold. It actively shaped the Earth's physical geography, its ecosystems, and the very course of human history. Its severity reminds us of the powerful natural forces driving long-term climate change on our planet. What is causing these monumental climate swings? The answer lies not on Earth, but in space. Our planet's climate is influenced by numerous factors, some of which operate over tens, even hundreds, of thousands of years. One of the most significant is the natural cycles of changes in the Earth's orbit and axial tilt, known as Milankovitch cycles. These cycles describe predictable, long-term changes in the celestial mechanics of Earth's motion around the Sun, which directly influence climate. They are considered the primary drivers of ice ages and warm interglacials. However, our planet's motion around the Sun determines not only the onset of ice ages, but also how solar heat is distributed across different parts of the globe. There are three main Milankovitch cycles that have a decisive influence on Earth's climate: eccentricity, axial tilt, and precession. Each of these cycles has its own period and influences the amount of solar radiation the planet receives at different latitudes and times of year. Eccentricity is, simply put, the shape of Earth's orbit around the Sun. This orbit is not a perfect circle, but an ellipse, a slightly elongated oval. The eccentricity cycle describes how elliptical this orbit becomes over time. It has a primary period of approximately 100,000 years and a secondary period of 400,000 years. As the orbit becomes more elongated, the distance between Earth and the Sun varies more significantly throughout the year. This means that the difference in the amount of solar energy received at perihelion, when Earth is closest to the Sun, and at aphelion, when it is farthest, becomes more noticeable. Although the total amount of solar energy received over the year changes only slightly, this greatly affects the length and severity of the seasons. For example, if Earth is closest to the Sun during the Northern Hemisphere summer, that summer will be hotter and shorter. Second, the Earth's axial tilt. This describes the angle at which our planet's axis of rotation is tilted relative to the plane of its orbit. Currently, this tilt is approximately 23.5 degrees, but it is not constant, fluctuating between 22.1 and 24.5 degrees. This tilt cycle lasts approximately 41,000 years. It is the axial tilt that determines the seasons on Earth. The greater the tilt, the more extreme the seasons become. Summers become hotter and winters become colder. But here's the interesting thing. Mild, cool summers are more important for glacier formation than harsh winters. If summer temperatures aren't high enough to melt the snow and ice accumulated during the previous winter, they begin to accumulate year after year, eventually turning into giant glaciers. Thus, it is the decreasing axial tilt that promotes milder summers at high latitudes, which typically triggers the growth of ice sheets. And finally, the third phenomenon is precession. This movement of the Earth can be compared to the wobble of a spinning top that begins to slow down. This wobble changes the direction of the Earth's axis of rotation relative to distant stars. The precession cycle consists of two main components, with periods of 18,000 years and... Imagine our planet not as a stationary sphere, but as a giant spaceship, making its eternal journey through the void. This ship doesn't just fly in a straight line. It dances, it wobbles, tilts, and changes its trajectory in a grand celestial ballet. One of these dance cycles, the axial wobble, takes from 19,000 to 23,000 years. The other, the change in tilt, lasts about 41,000 years, and a complete cycle of orbital change takes a full 100,000 years. It is this cosmic dance that dictates the rules of the game for the seasons on our planet. After all, the seasons are a direct consequence of where Earth is in its elongated elliptical orbit. Fast forward to today. Right now, summer in the Northern Hemisphere occurs when our planet is at its farthest point from the Sun, at what's known as aphelion. This factor makes our northern climate more moderate, smoothing out peaks in heat. But let's rewind time, about 11,000 years. During the previous Great Cycle, things were different. Summer occurred when Earth, on the contrary, was at its closest approach to the Sun, at perihelion. And this meant that the summer months were much hotter. The combination of these two great cycles, the shape of the orbit and the wobble of the axis, creates a phenomenon that scientists call the precession of the equinoxes. Essentially, this determines which hemisphere will experience the hot summer when the Earth is closest to its star. And herein lies the key to understanding ice ages. For giant ice caps to begin their inexorable growth, one simple condition is needed: a cool summer in the northern latitudes, a summer that cannot melt all the snow and ice accumulate over the long winter. It is the combined effect of these three great cosmic cycles that creates climate conditions on Earth that last for millennia. The amount of solar heat received by different parts of our planet at different times of the year varies enormously. Although the total amount of energy the Sun gives to the Earth remains virtually constant, its distribution across the surface is a completely different story. These changes are especially striking in the high northern latitudes during the summer months. It is these seemingly insignificant fluctuations that trigger the onset and end of great glaciations. The Northern Hemisphere plays a central role in this drama. Why? It's simple. It's home to the majority of land, vast continental masses that could serve as a springboard for ice advances. If northern lands receive less solar energy in the height of summer, the chances of winter snow surviving the warm season increase dramatically. This allows the snow to accumulate year after year, layer after layer, until its own weight compresses it into glacial ice, creating colossal glaciers. And once ice sheets begin to form, they trigger a chain reaction. So-called positive feedback loops are triggered, which only exacerbate the cooling. Imagine a giant white mirror. The shiny surface of the ice, with its high albedo, reflects most of the sun's rays back into space. The Earth absorbs less heat, becomes even colder, and the ice cover expands even further. The theory, named after Serbian scientist Milutin Milankovic, explains the chronology of glacial and interglacial periods of the past with astonishing accuracy. We find evidence of this in the planet's geological record, in deep-sea marine sediments and ice cores extracted from Antarctica and Greenland. Like time capsules, they preserve information about the climate of the distant past. Of course, there were other factors: supervolcanic eruptions, changing greenhouse gas concentrations, and continental movement. But Milankovic's theory remains the primary tool for understanding the great climate swings of the past. These cycles are nothing less than the fundamental mechanism responsible for global oscillations between the world of ice and the world of warmth. They provide us with a predictable astronomical basis for peering into Earth's past and understanding the rhythm of its glacial heart. The key to this story is the relationship between solar energy and Earth's ice caps. It's not a matter of the sun itself suddenly becoming dimmer. No, it's how our planet receives and distributes this heat. These subtle yet critical changes, dictated by Milankovitch orbital cycles, have a dramatic impact on the growth and retreat of ice sheets. The amount of solar radiation, or insolation, Earth receives becomes the decisive factor determining the fate of its icy shell. For the ice sheet to begin growing, more snow must fall during the winter than melt during the summer. If summer temperatures are too high, all the winter snow will disappear without a trace, and no accumulation will occur. But if the summer is cool enough for some snow and ice to survive the melting season, a new layer will fall on top of it the following year. Year after year, the snow will accumulate, compacting under its own weight, and eventually turning into a monolithic ice sheet kilometers thick. And this process is most effective in the high latitudes of the northern hemisphere, where vast expanses of land serve as the ideal foundation for ice giants. And here, Milankovitch cycles come into play again, like a conductor governing the amount of sunlight reaching these critical regions in the summer. Let's take a closer look at each of these cosmic rhythms. First, there's eccentricity, the degree of eccentricity of Earth's orbit. This parameter changes over a cycle of approximately 100,000 years. As the orbit becomes more elliptical, the difference in distances to the Sun at its closest point, perihelion, and furthest point, aphelion, becomes much more significant. If summer in the northern hemisphere occurs when Earth passes close to the Sun, it will be hot, but if the planet is at its farthest point at this moment, the summer will be cool. These cool summers are the ideal conditions for glacier growth, as they dramatically reduce melting rates. Secondly, the tilt of the Earth's axis. It is also not constant, fluctuating between 22.1 and 24.5 degrees with a cycle of approximately 41,000 years. This tilt directly influences the severity of the seasons. The greater the tilt, the more contrasting the seasons. Summers become scorching hot, and winters are icy cold. With a smaller tilt, the opposite occurs. The climate moderates. Summers become cooler and winters warmer. And for glacier growth, a smaller tilt is a real boon. High latitudes receive less direct sunlight in the summer, which leads to less intense heating and, consequently, less melting. This effect of cool summers is far more important than the effect of warmer winters on ice accumulation. And finally, the third factor is precession, that slow wobble of the Earth's axis, similar to the swing of a top. With cycles of 19,000 and 23,000 years, this phenomenon determines when certain seasons will occur in the Earth's orbital path. Today, as we've already mentioned, summer in the northern hemisphere occurs when the Earth is farthest from the Sun. This makes our summers comparatively mild. But just 11,000 years ago, the opposite was true. Northern summers occurred at perihelion, the moment of closest approach to the sun, leading to a hotter climate. For ice sheets, the ideal scenario is when summer in high northern latitudes coincides with the passage of the farthest point from the sun on an elongated eccentric orbit. This combination creates particularly cool conditions, literally fueling ice growth. When all these orbital factors come together, they can trigger an ice age. With minimal summer sun in the north, conditions are ideal for snow and ice to survive the summer year after year. This leads to the accumulation and formation of massive ice sheets, which begin to spread across the continents. Once again, positive feedback comes into play. Giant white fields of ice and snow, as we recall, act like a high albedo mirror, reflecting sunlight back into space. This reduces the amount of heat absorbed by the planet, which, in turn, leads to further cooling and even greater ice growth. Furthermore, the appearance of continent-sized ice sheets alters the paths of atmospheric and ocean currents, further influencing the climate. But the pendulum also swings in the opposite direction. When orbital cycles align so that northern latitudes receive maximum solar heat in summer, a great retreat begins. Existing ice sheets begin to melt, faster than new snow can accumulate. And here, too, there's a feedback mechanism. As the ice melts, it exposes the dark surface of land or ocean beneath. Dark surfaces, unlike white ones, absorb much more solar energy. This leads to further warming and even more rapid melting. It is these dramatic changes in Earth's orbit, dictated by celestial mechanics, that explain the rhythm of glacial and interglacial periods that we see in the geological record of the last several million years. These seemingly small and slow changes in the way the Earth rotates, tilts, and travels around the sun are the primary external factor triggering dramatic oscillations between periods of total glaciation and periods of global warming. Let's travel back in time, to the era when our world was emerging from its icy captivity. The transition from the harsh conditions of the Ice Age to the warmth we experience today didn't happen overnight. It wasn't a sudden flip of a switch that instantly melted centuries of ice. No, this process began with subtle, almost invisible changes in Earth's gigantic climate machine. Imagine these first, timid signs of impending warming. At first glance, they seemed insignificant, but in fact, they were the harbingers of a colossal transformation. They heralded a planetary-scale drama that would ultimately melt vast ice sheets, forever alter the contours of continents, and reshape entire ecosystems. And what was the trigger? The main impetus for this process was provided by slow but inexorable changes in our planet's orbit and axial tilt. These cosmic cycles affected the distribution of solar energy, reaching key latitudes on Earth. One of the earliest and most obvious signals of impending warmth was the gradual rise in average temperatures around the world. At the height of the last glacial maximum, the planet was gripped by temperatures some 8 to 10 degrees Celsius lower than what we experience today. However, the retreat from this extreme cold began long before the world became recognizable. Scientific reconstructions based on the analysis of ice cores, ice samples extracted from deep boreholes in Greenland and Antarctica, show a clear trend. Atmospheric temperatures began their slow rise approximately 20,000 years ago, and some evidence suggests this process may have begun even earlier. These ice cores are more than just frozen water. They are a priceless record of the past, a veritable archive of the ancient atmosphere. The composition of the ice, particularly the ratio of oxygen isotopes, serves as a kind of thermometer for scientists. Increased proportions of certain isotopes directly indicate that the planet was warming at the time this snow fell. However, it's important to understand that this warming was not uniform across the globe. In some regions, it was much faster and more intense, especially at high latitudes, where giant ice sheets exerted the strongest influence on the climate. Another key sign of impending change is the changing chemical composition of the atmosphere. Specifically, this concerns the increasing concentration of greenhouse gases. Data obtained from those same ice cores provides irrefutable evidence. Levels of carbon dioxide and methane, two powerful greenhouse gases, began to rise from glacial lows around the same time global temperatures began to rise. At the glacial maximum, atmospheric carbon dioxide concentrations were critically low, around 180 parts per million. To put this into perspective, this is significantly lower than even pre-industrial levels, which were approximately 280 parts per million. As the Earth slowly began to warm, natural processes began releasing these gases back into the atmosphere. For example, rising ocean temperatures led to the release of massive amounts of dissolved carbon dioxide. Changes in global ocean currents may also have played a role, bringing carbon from deep-sea reservoirs to the surface. Scientists believe the rise in methane levels was linked to the expansion of swamps and wetlands that emerged as glaciers melted, revealing new land. Another source is the decomposition of ancient organic matter trapped in permafrost for millennia. Rising greenhouse gas levels have created a powerful positive feedback loop. Imagine a chain reaction. The Earth warms due to changes in its orbit. This heat releases even more greenhouse gases, which in turn further accelerate the warming trend. The plant world also began to send its own, albeit subtle, signals. As temperatures gradually rose, especially in areas adjacent to glaciers and on the edges of the vast tundra, the familiar landscape began to change. Cold-tolerant plant species retreated north and were replaced by those preferring a more temperate climate. Analysis of fossil pollen preserved in lake and bog sediments reveals this gradual changing of the guard. We see how, in some areas, harsh tundra grasses and sedges gave way first to shrubs and then to pioneer trees such as birch and pine. These could still tolerate cool conditions, but they now required more heat than tundra plants. This botanical transition was a slow process, spread over centuries, but it was fundamental evidence that the regional climate was shifting toward warmer, wetter conditions capable of supporting far more complex and diverse plant communities. Data from ocean floor sediments also serve as an early indicator of warming. Changes in the types of microscopic fossils found in these layers, such as the shells of tiny marine organisms, can reveal a wealth of information about fluctuations in ocean temperature and currents. We see how the North Atlantic began to receive increasing amounts of fresh meltwater from retreating glaciers. This influx could have significantly impacted ocean circulation, potentially leading to even more rapid warming in certain regions. Deep ocean currents, which play a key role in distributing heat across the planet like a giant conveyor belt, began to reorganize and adapt to changes in ice cover, contributing to global warming. And, of course, the first signs of the retreat of the glaciers themselves, though imperceptible to the eye of ancient humans, were the most important symptom of the planet's awakening. As average summer temperatures gradually increased, less and less snow and ice survived the melting season at the edges of the vast ice sheets and in mountain glaciers. This led to a very slow but steady thinning and retreat of the ice fields, eventually culminating in massive melting. During the initial stages of this process, there was likely an increase in meltwater flows flowing from the glacial fronts. This water formed new periglacial lakes or altered the courses of ancient rivers, causing them to overflow their banks. These early, almost invisible changes in the ice mass balance were a direct consequence of the slight but steady increase in solar radiation reaching high northern latitudes. This orbital influence, this cosmic metronome, signaled the beginning of the end of the Great Cooling. The Earth was slowly but surely awakening from its long, icy slumber. The end of the last glacial maximum, which began approximately 19,000 years ago, was marked by the rapid melting of the enormous ice sheets and mountain glaciers that covered vast swathes of our planet. This process, known as deglaciation, was an incredibly dynamic and transformative event. It profoundly altered landscapes, created new river and lake systems, and, in essence, laid the foundation for the modern world. Initially, the retreat of the ice was gradual, But as temperatures continued to rise, the melting accelerated, becoming an unstoppable process. The primary driver of this global thaw was the retreat of massive continental ice sheets, such as the Laurentide ice sheet in North America and the Scandinavian ice sheet in Europe. Rising global temperatures, driven by changes in Earth's orbit and rising greenhouse gas concentrations, upset this delicate balance. Summers became warm enough to melt far more snow and ice than had accumulated during the preceding harsh winters. This led to a net loss of ice mass and a reduction in glacier size. The ice sheets weren't simply melting in place, their edges were actively retreating northward. Although this retreat was often interrupted by brief periods of temporary cold snaps, the overall trend was clear. The icy world was shrinking. As the ice sheets retreated, they left behind a radically altered, literally plowed-up landscape. The unimaginable mass of ice, weighing trillions of tons, acted like a giant bulldozer, scraping away bedrock, creating wide valleys, cirques, and deep fjords. As the ice melted, it released vast quantities of rock and sediments that had been frozen within its core. These materials remained on the surface as various landforms. Moraine ridges, known as till ridges, are mounds of unsorted glacial sediment that precisely mark the former boundaries of the ice. Drumlins, elongated hills resembling inverted spoons, also bear witness to this great retreat. Vast areas covered in sand and gravel were formed by powerful flows of glacial meltwater. These sediments, carried by rivers flowing from the ice front, completely changed the topography of entire regions previously buried under a kilometer-thick layer of ice. One of the most significant and spectacular consequences of the retreating ice was the emergence of new lakes. As the ice sheets melted, they accumulated enormous quantities of meltwater, which filled depressions carved by glaciers or were blocked by ice dams. These periglacial lakes often reached colossal sizes. Many of them would dwarf most modern lakes. The most striking example is glacial Lake Agassiz, which covered parts of the modern-day Canadian provinces of Manitoba and Saskatchewan, as well as the U.S. state of North Dakota. At its peak, Lake Agassiz was larger than all of North America's Great Lakes combined. These giant lakes served as temporary reservoirs. Meltwater accumulated within them, but the sudden collapse of an ice dam or the emergence of new runoff could lead to catastrophic floods of biblical proportions. Melting ice was changing the world, but the advance of giant glaciers brought more than just destruction. It became a great sculptor, forever reshaping the planet's river map. Imagine ancient rivers flowing along their channels for millennia, and now a wall of ice kilometers high is advancing on them. The old routes were mercilessly erased from the face of the earth, buried under a monstrous mass of frozen water. When the ice began to retreat, we witnessed the birth of an entirely new water network. Streams of meltwater, turbid and laden with rocks and sand, rushed away from the ice walls. They carved new paths for themselves, winding through the land and creating endless river valleys. Many of the great rivers we know today, in regions once frozen over, owe their origins to these colossal flows of meltwater. Take the mighty Mississippi River, for example. Its modern system was largely shaped by enormous volumes of meltwater, which carried billions of tons of sediment south from the melting Laurentide ice sheet. These enormous flows, freed from their icy confines, sometimes had truly catastrophic consequences, transforming landscapes and creating the hydrological landscape we observe to this day. But it's wrong to think that glacier retreat was a simple, one-dimensional process. The planet's history at that time resembled a seesaw. There were moments when winter seemed to be returning with renewed, ferocious force. Science knows of periods of abrupt climate upheavals, one of which was the Younger Dryas, which began approximately 12,900 years ago and lasted over 1,000 years. Over the course of this millennium, temperatures in the northern hemisphere plummeted to near glacial levels. The great melt halted, glaciers that had already begun to retreat froze, and in some regions even resumed their advance. This was a clear example of how fragile and unpredictable Earth's climate system was during that era. However, the Ice Age was doomed. After this temporary respite, warming resumed with renewed vigor. The final and rapid melting of the remaining ice giants began. The scale of this process is truly staggering. In North America, the colossal Laurentide ice sheet, which covered almost the entire continent, almost completely disappeared in just a few thousand years. By 10,000 years ago, only a small fragment remained, and by 7,000 years ago, it had completely melted. A similar fate awaited its European counterpart, the Scandinavian ice sheet. Its melting gave us the unique fjords of Scandinavia and shaped the modern appearance of the British Isles. Around the world, mountain glaciers also retreated, feeding rivers and contributing to global climate change. This great melt was a geological force of incredible power. It not only caused a global rise in sea levels, but also left scars and gifts on the face of our planet that we still see today. Fertile soils brought by glaciers, countless lakes carved by their mass, and completely rebuilt river systems. All these are the legacy of the Ice Age, defining the shape of the modern world. The moderate climate we consider normal was a direct consequence of these events, influencing everything from where people could settle to how they managed their livelihoods. One of the most dramatic and terrifying consequences of this great melting was the rise of the world's oceans. This wasn't just a slow rise in sea levels, it was a veritable global flood that completely reshaped the coastlines of the continents, inundated vast areas that were once dry land, and had a colossal impact on ecosystems and early human civilizations. The scale of this event was truly titanic, surpassing anything humanity had ever seen in its history. The geography of our planet was rewritten. Fast forward to the last glacial maximum, approximately 20,000 to 26,000 years ago. The world looked completely different. Scientists estimate that sea levels were 120 meters lower than they are today. Just imagine, that's the height of a 40-story building. This colossal drop in sea levels was easily explained. Billions of cubic meters of water were frozen in the giant ice sheets that covered North America and Europe, as well as in the expanding mountain glaciers. To understand the scale, it's enough to say that if all the ice on the planet melted today, sea levels would rise by approximately 66 meters, inundating all coastal cities. And so, when the Earth began to warm approximately 19,000 years ago, this gigantic ice reservoir began to melt. Trillions of tons of fresh water rushed from the continents back into the oceans. This process caused an inexorable rise in global sea levels. However, this rise was not smooth and uniform. It occurred in spurts, sudden and devastating surges that corresponded to abrupt climate changes. History records several such periods when ice sheets disintegrated at catastrophic rates. One such event is known as Meltwater Pulse 1A, which occurred approximately 14,500 years ago. Consider these numbers. In just 500 years, sea levels rose by as much as 20 meters, according to some estimates. That's a rate that could be observed within a single human lifetime. This wasn't just a change, it was a true catastrophe for all coastal life. The most obvious consequence of this process was the submergence of coastal plains and continental shelves. During the Ice Age, these vast, gently sloping areas of the seafloor were dry land, expanding the continents far beyond their current limits. These shelf zones were often extremely rich in resources, supporting unique ecosystems and providing invaluable habitats for ancient animals and people. But as the ocean advanced, these low-lying lands were submerged one by one. This meant that the vast hunting grounds, fertile plains, and coastal camps used by our ancestors were forever swallowed by the sea. Studying archaeological sites on the ocean floor is incredibly difficult, but the little information we have suggests a significant human presence in these submerged worlds. The encroaching sea also destroyed the land bridges that had served for centuries as corridors for the migration of animals and people between the continents. The famous Bering Land Bridge, connecting Asia and North America, slowly sank until this vital migration route was finally severed around 11,000 years ago. Similarly, the Sunda Sea, a gigantic landmass connecting mainland Southeast Asia with its islands, sank, leading to the isolation of numerous populations. Doggerland, the land that connected Britain with continental Europe, was also submerged. In its place, the English Channel formed, forever separating the British Isles. These events altered the evolutionary paths of species and divided human cultures. For ancient people, this was an era of great migration. Coastal communities, whose livelihoods depended on the abundant bounty of the sea, were forced to continually retreat inland, fleeing the encroaching waters. Imagine a constant flight, generation after generation, from a coastline inexorably moving inland. This created enormous difficulties for survival and maintaining social ties. And although melting glaciers opened up new lands to the north, the loss of these rich coastal zones was a grave challenge to which humans had to adapt. In addition to direct flooding, rising sea levels completely reshaped coastal ecosystems. River mouths, vital nurseries for many marine species, were forced inland. Saltwater infiltrated coastal freshwater supplies, poisoning sources vital to humans and animals. The entire coastal environment and its resources were completely rebuilt. This entire transition from the low sea levels of the Ice Age to the modern era took approximately 12,000 to 15,000 years, at an average rate of about a meter per century. But, as we have already seen, this process was punctuated by periods of much more rapid and catastrophic upwelling. This historical lesson serves as a reminder of how dynamic the Earth's climate system is and the consequences of even seemingly minor changes. But melting ice produced more than just a slow ocean advance. Sometimes it led to catastrophes of truly biblical proportions. The melting process didn't always flow like a trickle. In many parts of the world, gigantic volumes of meltwater accumulated in enormous lakes, impounded by natural ice dams. But these ice barriers were temporary. When they couldn't withstand the colossal pressure, they collapsed, unleashing torrents of fresh water of a magnitude the world had never seen before. In a matter of days or even hours, these massive floods reshaped the landscape. These weren't just floods, they were events of apocalyptic proportions. Floods of such power that they stripped rocks to their very foundations, carved gigantic canyons into the earth, and carried boulders the size of houses for hundreds of kilometers. And the most striking, best-studied example of such an event was the Great Missoula Floods, which repeatedly swept across northwestern North America approximately 15,000 to 13,000 years ago. The source of these monstrous floods was Glacial Lake Missoula, a gigantic body of water that formed at the edge of the ice sheet. Let's go back in time to an era when the world was shedding its shackles of ice. Before us stretches the colossal Cordilleran ice sheet, a gigantic mass of ice covering the western part of modern-day Montana. Imagine this scene, a tongue of ice, inexorably sliding south, cutting into the Clark Fork River Valley, creating a natural but monstrous barrier. This ice dam is more than just a block of ice. It's a wall over 600 meters high, taller than any modern skyscraper, and tens of kilometers wide. It completely blocks the flow of the mighty river. Deprived of its natural outlet, the water begins to accumulate. Day after day, year after year, the water level rises, and the gigantic glacial lake Missoula emerges. At its peak, this lake was a veritable inland sea. Its depths held over 2,000 cubic kilometers of water, a volume comparable to half the size of Lake Michigan. The expanse of water stretched over an area of 7,500 square kilometers, and in some places the depth reached the same monstrous 600 meters. But this icy prison for trillions of tons of water was unstable. The incredible pressure of the water masses constantly tested its strength. Water, as we know, finds a way. It seeped into the tiniest cracks in the ice, froze there, and, expanding, acted like millions of tiny wedges. This process, known as hydraulic fracturing, slowly but surely eroded the dam from within. And then comes the fateful moment. The cracks merge and the ice barrier collapses with a deafening crash. All the pent-up power of Lake Missoula is released. In a matter of days, this gigantic sea is completely emptied. A torrent of water of unimaginable force, rushing at speeds of up to 100 kilometers per hour, rushes through the lands of eastern Washington, carving a path through the Columbia River Gorge directly to the Pacific Ocean. To grasp the scale of this catastrophe, imagine all the world's rivers merging into a single stream. Now multiply that force tenfold. Or imagine the mighty Amazon and increase its flow 100-fold. This is precisely the force that lashed the prehistoric landscape. This fury of water created a unique landscape that scientists today call channelized wastelands. A surreal scene unfolds before us. Deep, winding canyons, the dried-up beds of colossal waterfalls, and gigantic ripple marks on the ground. These waves, frozen in stone, reached 15 meters in height, and the distance between their crests was hundreds of meters. They are an eternal testimony to the incredible power of ancient floods. The flood literally peeled the skin off the planet. It washed away vast layers of fertile soil and bedrock, exposing ancient basalt slabs. The water carried gigantic boulders with it, transporting them hundreds of kilometers from their homelands and depositing them where its fury subsided. These traveling stones still serve as silent witnesses to the torrent's colossal force. But the most astonishing thing about this story is that this apocalypse was not a one-off event. Geological evidence tells a different, even more terrifying story. The ice dam rebuilt and burst again and again, perhaps more than 100 times over a period of 2,500 years. Each new flood reshaped the landscape, deepening canyons and depositing new layers of sediment. It was a relentless cycle. Ice builds a dam, the lake fills to the brim, and then the dam gives way, and the world is plunged once again into aquatic chaos. Similar catastrophes, though not always on such a scale, occurred across ice-bound North America. The draining of other periglacial lakes caused equally significant floods. For example, when the Laurentide ice sheet melted, Lake Agassiz was formed. It was even larger than Lake Missoula and covered vast areas of modern-day Canada and the United States. However, its history was different. Lake Agassiz did not disappear as a result of a single massive outburst event. It drained in a series of powerful tremors as ice barriers collapsed in various places or new drainage channels opened. Each such event released colossal volumes of fresh water into the Atlantic Ocean, which undoubtedly influenced the climate of the entire planet. Let's move on to Eurasia. Here, the melting of the Scandinavian ice sheet and other ice masses also led to large-scale floods. In Siberia and Eastern Europe, enormous proglacial lakes were born and then disappeared, radically altering the entire hydrological system of the region. Ice dam breaches created new river valleys and deepened old ones. Although the traces of these events are less studied than in America, the geological principle itself remains unchanged. Where giant glaciers meet terrain capable of retaining meltwater, there is always the potential for catastrophe. Studying these great floods reveals the true power of nature and the dynamic nature of the end of the Ice Age. We understand that this was not a story of gradual and peaceful melting. It was an era of violent episodic cataclysms. These powerful floods produced rapid and profound changes on the face of the Earth, shaping the very landscapes we see today. They altered river courses, redistributed sediments, and even influenced the very topography of entire regions. The scale of these events speaks to the colossal energy released as the Ice Age gave way to a warmer world. As the ice retreated, the Earth's crust itself began to move. Imagine the weight of ice sheets several kilometers thick. Under this enormous weight, the Earth's crust sank, sinking into the viscous mantle beneath. It's like a heavy object, leaving an indentation in a soft surface. Once the enormous mass of ice had disappeared, the crust slowly began to straighten out, rising back up. This process, called isostatic rebound, continues to this day in regions like Scandinavia and parts of North America, where the land is rising by a few millimeters per year. This slow rising of the continents could have had fiery consequences, triggering volcanic activity. The release of the icy load altered the stress in the Earth's crust. These changes affected existing faults and magma chambers deep underground. Essentially, the disappearance of the icy pressure facilitated the rise of magma to the surface. The pressure that held the molten rock back weakened, leading to what's known as decompression melting. Magma found it easier to break through old weak spots in the crust. Research shows a clear link between periods of rapid glacier melt and surges in volcanic activity. For example, in Iceland, which was buried under a thick layer of ice, the number of eruptions increased sharply after the ice retreated. Similar data exists for parts of North America and even Antarctica. The impact of these eruptions on climate at the end of the Ice Age is a complex and fascinating puzzle. Large volcanoes release enormous quantities of gases and tiny particles called aerosols into the atmosphere. Sulfur dioxide, one of these gases, reacts with oxygen to form sulfate aerosols. These particles, like billions of tiny mirrors, reflect sunlight back into space, causing temporary cooling on the Earth's surface. The ash also blocks sunlight. If a series of powerful eruptions occurred during a period of general warming, they could cause local or even regional cooling, wreaking havoc on climate processes. Some scientists even suggest that volcanic aerosols may have played a role in triggering the enigmatic period known as the Younger Dryas. This was an abrupt, short-lived return to glacial conditions. If a series of major eruptions occurred during this time, their cumulative cooling effect could have amplified other factors and triggered this climatic reversal. However, the primary cause of the Younger Dryas is most often attributed to changes in ocean circulation, caused by those very same gigantic flows of freshwater meltwater we've discussed. Imagine a world freed from the shackles of ice. But this awakening was far from peaceful. Enormous volcanoes, dormant for millennia under the colossal weight of glaciers, were beginning to awaken, and their fury was a direct consequence of this great melt. These fiery mountains had a colossal impact on the planet's transforming landscape. Each eruption reshaped the map of the world. New volcanic cones were born from the bowels of the Earth. Streams of hot lava flooded valleys, and layers of ash, like a shroud, covered vast territories. The interaction of volcanoes with retreating glaciers was particularly dramatic. Imagine a unique geological phenomenon, an eruption occurring directly beneath kilometers of ice. This subglacial activity was capable of melting enormous volumes of ice, leading to sudden, catastrophic floods known as Jökulhlaup, monstrous torrents of water erupting from beneath the ice cap with unimaginable force. Some volcanoes, long held in check by the pressure of glaciers, erupted with renewed vigor after their retreat, creating entire mountain ranges or forming vast plains of solidified volcanic rock. Ash and lava flows buried the landscapes created by the Ice Age. This led to the total destruction of forests, forced rivers to change their courses, and created entirely new ecological niches. The migration routes of ancient animals that had traversed these areas for centuries were blocked, forcing them to seek new routes in this changing world. To identify signs of this increased volcanic activity associated with melting ice, scientists require a profound understanding of geological processes. They study layers of ash trapped in ice cores and sedimentary rocks, and date the volcanic rocks to reconstruct the chronology of events, while the precise connection between the melting of glaciers and a specific burst of volcanic activity is still a matter of scientific debate. The underlying physical mechanism appears more than plausible. As trillions of tons of ice sheets disappeared from the continents, it led to a colossal shift in stress within the Earth's crust. This reduced pressure, potentially facilitating the movement of magma toward the surface and triggering eruptions. Thus, while the Ice Age was reshaping the Earth's crust externally, the planet's internal forces may have played an equally important role in shaping this new world, adding another layer of complexity to the picture of climate transition. But what if Earth's internal forces weren't the only players in this arena? What if the end of the Ice Age was written not on Earth, but in the frigid abyss of space? The idea that a cosmic impact, such as a comet or asteroid, could have ended an entire era remains one of the most intriguing and controversial hypotheses. Such an event, though incredibly rare, could cause instant and catastrophic changes in the environment. Therefore, researchers around the world are trying to determine whether an extraterrestrial visitor could have played a fateful role in the dramatic changes observed at the end of the last Ice Age. The most prominent theory linking space and climate is the Younger Dryas impact hypothesis. Imagine this: the planet is slowly emerging from an ice age, becoming warmer, but suddenly something goes wrong. The Younger Dryas was an abrupt and relatively brief return to near glacial conditions that struck the northern hemisphere about 12,900 years ago. This mysterious cold period lasted for approximately 1,300 years, after which global warming resumed. This sudden icy relapse, this temperature spike, interrupted the planet's overall process of emerging from an ice age. The hypothesis posits that a comet or asteroid was the cause. After breaking apart, this cosmic object either collided with Earth or exploded in the atmosphere, causing global environmental destruction and triggering the cold period. Proponents of this theory point to a number of pieces of evidence they interpret as traces of this monumental event. One key argument is the discovery of so-called impact markers in geological layers, which serve as a precise time marker for the onset of the Younger Dryas. These markers include nanodiamonds, microscopic crystals that can only form under the extreme pressures and temperatures characteristic of a collision. Magnetic spherules, tiny balls formed from molten rock, have also been found, as well as particles of charcoal and soot from global fires. But the most compelling clue is the elevated levels of platinum and iridium in sediments from that period found in North America, Europe, and the Middle East. These elements are extremely rare on the Earth's surface, but are abundant in asteroids and comets. These materials were found in a special layer, sometimes called the Younger Dryas boundary layer. The widespread occurrence of these markers, often associated with a dark layer rich in organic material, may indicate a continental scale event, a powerful airburst, or a direct impact with the surface. The consequences of such an impact or airburst would be truly apocalyptic. Imagine an event similar to the Tunguska meteorite of 1908, but on a continent-wide scale, or even many times larger. This would lead to widespread forest fires across North America. These fires, in turn, would cause irreversible damage to the entire planet's ecosystem. Colossal amounts of soot and dust would be released into the atmosphere, creating a dense curtain that would block out sunlight for years. This, in turn, would trigger a nuclear winter and a sharp drop in temperatures worldwide. Such a rapid cooling event could have triggered the onset of the Younger Dryas, disrupting natural atmospheric circulation and, more importantly, affecting ocean currents. One such change could have been the disruption of the Atlantic Meridional Circulation, AMC, a giant ocean conveyor belt that plays a key role in heat distribution in the North Atlantic. Furthermore, it is hypothesized that the impact could have destabilized the Laurentia ice sheet, which covered much of North America. This would have caused a sudden and massive release of freshwater meltwater into the North Atlantic. This influx of freshwater could have literally halted circulation, upsetting the entire climatic balance. This mechanism is now considered one of the most likely causes of the Great Cooling Event. The sudden influx of huge masses of cold freshwater would have reduced the density of surface water, preventing it from sinking to depth and thereby breaking the chain of warm currents moving northward. However, the cosmic impact hypothesis remains the subject of fierce debate in the scientific community. Many scientists, while acknowledging the reality of the Younger Dryas period itself, question the evidence for an extraterrestrial impact as its primary cause. Critics argue that many of the proposed impact markers, such as nanodiamonds or soot, are not unique and could have formed as a result of other natural processes, such as ordinary forest fires or volcanic activity. They also point to inconsistencies in the dating of some finds and, most importantly, the lack of a clear impact crater of the appropriate age and size. There are also alternative explanations for the onset of the Younger Dryas that don't require space intervention. They involve changes in ocean circulation caused by the influx of fresh water from the natural melting of ice sheets. For example, the outburst of the giant glacial lake Agassiz could have released enough fresh water into the ocean to disrupt the climate balance. These explanations are well supported by climate modeling and geological data. While debate continues, the cometary impact hypothesis itself highlights how vulnerable our planet is to sudden extraterrestrial events that could dramatically impact Earth's climate and landscapes. If such an event did occur, it would not have directly caused the end of the Ice Age. The overall warming trend was driven by changes in Earth's orbit. However, it could have caused a significant temporary reversal in this trend, profoundly affecting the fate of Ice Age organisms and the lives of early human populations. Careful scientific investigation of this hypothesis opens new horizons in science, deepening our understanding of Earth's complex past and the many factors that may drive climate change. The Younger Dryas was a sudden and abrupt cold spell, almost reaching glacial levels, that interrupted the overall warming trend at the end of the last Ice Age. This period of abrupt cooling began about 12,900 years ago and lasted for approximately 1,300 years, after which rapid warming resumed, marking the beginning of our current warm interglacial period. The Younger Dryas is a key event for understanding the climate past. It demonstrates how quickly Earth's climate system can switch gears, even when the overall trend is in the opposite direction. To understand the full shock of this event, let's travel back to the world just before the catastrophe. Before the Younger Dryas, Earth had been steadily warming for several millennia since the peak of the last glaciation. The planet was experiencing a warming epoch. Vast ice sheets melted, sea levels rose, and vegetation zones shifted north. This phase, known as the Bölling-Allerud interstadial, was characterized by relatively mild conditions, especially in the northern hemisphere. However then, almost overnight, some regions, such as the North Atlantic, experienced a sharp cooling. Conditions approached those of the glacial maximum. According to ice core data from Greenland, average annual temperatures dropped by as much as 10 to 15 degrees Celsius in just a few decades. This rapid cooling had widespread consequences. Glaciers that had been retreating suddenly began to advance again. Vegetation reverted to cold-resistant species, and sea ice once again encased the vast expanses of the North Atlantic. The most widespread theory explaining this event: imagine this. The ice ages that had held the planet in their cold grip are beginning to weaken. But this process is interrupted by a significant disruption in the Atlantic Ocean circulation system. This disruption is directly related to a phenomenon scientists call the AMOC, or Atlantic Meridional Overturning Circulation, essentially a giant ocean conveyor belt. What is this conveyor belt? It's a colossal system of currents, a veritable river current within the ocean, tirelessly transporting warm, salty water from the tropical latitudes far north into the harsh waters of the North Atlantic. When this warm current reaches cold regions, it releases its heat to the atmosphere, cools, becomes denser and heavier, and then sinks into the depths. This sinking, in turn, creates a pull that draws in new portions of warm water from the south. This enormous mechanism acts like a giant furnace, moderating the climate in Western Europe and parts of the North American continent, making these lands much warmer than other regions at the same latitude. Now let's fast forward to the era of melting great glaciers that preceded the cooling period known as the Younger Dryas. The retreating ice sheets left behind gigantic meltwater lakes. One of these, the largest, was named Lake Agassiz. It was a true freshwater sea, stretching across the heart of North America and covering an unimaginable area. Geological evidence tells a dramatic story. About 12,900 years ago, a gigantic ice dam broke in this gigantic Lake Agassiz, likely through the Great Lakes system and the St. Lawrence River. A monstrous torrent of icy fresh water poured into the North Atlantic. This massive influx radically altered the ocean's chemistry, dramatically lowering the salinity of its surface waters. And therein lay the catastrophe. Freshwater is much less dense than saltwater. It simply couldn't sink to the depths as effectively as the usual cold, salty water. This disruption suddenly slowed and possibly completely halted the AMOC ocean conveyor belt. Effectively, someone turned off the giant heat pump that warmed the entire North Atlantic region. Without this heat transfer from the south, the North Atlantic and adjacent continents rapidly reverted to a glacial state. Sea ice crept southward, expanding its reach, its white surface reflecting sunlight back into space, further cooling the planet. This regional glacial shock was so powerful that it triggered a chain reaction worldwide, altering atmospheric flow patterns and triggering droughts in tropical regions. The monsoon system collapsed. We find evidence of this oceanic catastrophe today on the seafloor in sediment cores. They show how the composition of microorganisms changed. Heat-loving species disappeared, giving way to cold-tolerant ones, and the composition of the sediment itself indicates a dramatic shift in ocean currents. While the freshwater lake outburst scenario is the leading explanation for this cataclysm, other, more exotic hypotheses exist. One of them, though less popular in the scientific community, is the cosmic impact hypothesis. According to it, the sudden cold snap could have been caused by a comet exploding in Earth's atmosphere. Supporters of this theory, as mentioned earlier, point to the discovered markers of such an event, traces of large-scale forest fires and the sudden climate change itself. However, most scientists consider this evidence unconvincing, arguing that the freshwater outburst mechanism provides a much more logical and factual explanation for everything that happened. The event we call the Younger Dryas serves as a stark reminder of how sensitive our planet's climate system is to sudden changes, especially when it comes to something as fundamental as ocean circulation. It clearly demonstrates that the transition from the Ice Age was not a smooth and gradual warming. Instead, it was accompanied by extreme and abrupt climate swings. The lessons we learn from this distant era are incredibly important for understanding potential future climate change. They show that even amidst global warming, local or even global catastrophic cooling can occur if certain tipping points in Earth's systems are passed. That massive influx of fresh water caused by melting glaciers forever altered ocean currents. And this ancient event is striking evidence of the complexity and sometimes unpredictability of our planet's climate. Approximately 12,000 years ago, the last ice age ended, marking a turning point for the planet's entire ecosystem. It was during this period that a mass extinction of numerous species of giant animals, collectively known as megafauna, occurred. This process affected all continents, but its consequences were particularly devastating for North and South America, as well as for much of Eurasia. Understanding why and how this catastrophe occurred is one of the central tasks of paleontology and archaeology, where scientists are attempting to unravel the complex web of factors. Megafauna are generally defined as large animals, typically weighing over 45 kilograms. The Ice Age was their era, their world. Pleistocene North America was home to true titans, woolly mammoths, mastodons, saber-toothed cats, dire wolves, giant ground sloths, short-faced bears, and even American camels. But today, we can only see them as fossils. All of them have disappeared from the face of the Earth. South America saw an equally tragic picture. Various species of giant sloths, glyptodonts, armored beasts the size of cars, elephant-like Gomphotheres, and rhinoceros-like Toxodon became extinct. Smaller animals disappeared along with them. In Eurasia, the same fate befell woolly rhinoceroses, cave bears, and cave lions. However, some megafauna, such as reindeer and bison, managed to survive. In Africa and some regions of South Asia, the extinction was less widespread, and many large animals, including elephants and rhinoceroses, survive to this day. The timing of these extinctions is crucial. In North and South America, everything happened instantly, geologically speaking. The catastrophe coincided with the end of the Dryas period, approximately 10,000 years ago, and with the arrival of the first modern humans on the continent. In Eurasia, the process was more drawn out. Some species disappeared earlier, others later, but the very speed and nature of these extinctions indicate colossal pressure from the environment or, possibly, human activity. Scientists have put forward several main hypotheses to explain this great loss. While emphasis is often placed on a single cause, many researchers today tend to believe it was a combination of several lethal factors. There are two main theories explaining the causes of the extinction. The first is global climate change. The second is human influence, specifically hunting. According to the climate hypothesis, the main cause of the giants' demise was the rapid warming and environmental shifts at the end of the Ice Age. As the ice caps melted, the planet's landscapes began to change dramatically. Vast, fertile mammoth steppes and cold meadows, which had supported countless herds of large herbivores, began to disappear. In their place, dense forests grew, or new types of swamps and shrublands appeared. This shift in vegetation led to the disappearance of the food supply for highly specialized animals such as mammoths and woolly rhinoceroses. Moreover, the sudden warming intensified the climate's seasonality. Summers became hotter and winters colder. Many animals simply couldn't adapt to such dramatic changes. Melting glaciers caused massive floods and rising sea levels, altering habitats and isolating animal populations. New diseases, carried by animals or even humans, may have emerged, potentially decimating stress-weakened megafauna populations. It is believed that many of these giants were ideally suited to the cold and open world of the Ice Age and were simply unable to adapt to the speed and scale of their changing world. Another hypothesis, known as the overkill theory, places the blame on humans. It proposes that early modern humans were the primary cause of extinction, particularly on continents like the Americas, where humans emerged as a completely new and incredibly effective predator. When humans first arrived in the Americas around 15,000 years ago, they encountered a world inhabited by gigantic animals that were completely unprepared for their arrival. These animals likely had no defensive instincts against a predator that acted as humans did. Humans, on the other hand, were armed with advanced stone tools for the era and mastered deadly hunting strategies. They used projectile weapons such as spears and later bows and arrows, allowing them to hunt the largest and most dangerous animals without engaging in close combat. The rapid expansion of humans across North and South America, which coincides perfectly with the megafauna extinction event, is a key argument in favor of this theory. According to this hypothesis, hunting pressure was exacerbated by a blitzkrieg effect. Hunters rapidly advanced into new territories, decimating intact populations that the slowly reproducing giants simply did not have time to replenish. The fact that in Africa and parts of Asia, where megafauna coexisted with human ancestors for millions of years, the extinction was less widespread only supports this hypothesis. The prolonged evolutionary confrontation likely forced African giants to develop more effective survival strategies against the planet's most dangerous predator. There is a third point of view, which is gaining more support today. Today, most paleontologists lean toward an idea that resembles a perfect storm scenario. This theory posits that no single factor, neither the merciless climate nor the emergence of a new predator, humans, could have wiped out an entire army of giants. It was their deadly alliance, the devastating effect they produced when they struck simultaneously. Imagine, a climate changing at breakneck speed dealt the first devastating blow to megafauna populations. It brought them to their knees. The world they knew began to crumble. Their once blessed hunting grounds and grazing lands became isolated pockets of life, and their food supply rapidly dwindled. To make matters worse, weakened by hunger and stress, the animals became easy prey for new, previously unseen diseases. And at this very moment, when the giants were already teetering on the brink of survival, a new player entered the picture: humans. Incredibly intelligent, organized, and deadly hunters. Even the slightest intervention on their part became the last straw for the weakened populations, the very push that sent them into the abyss of oblivion. Collapse was inevitable. Let's consider a simple example. Global warming is shrinking a species' natural habitat, forcing the surviving animals into tiny pockets of land. Here, in this natural trap, they become incredibly easy targets for hunters. The disappearance of these titans was a turning point in the planet's history, forever altering the face of global ecosystems. When the enormous herbivores and the predators that followed them disappeared from the scene, everything changed: the structure of the vegetation, the natural cycle of matter, and, of course, the delicate balance between hunter and prey. Studying this ancient catastrophe is more than just a glimpse into the past. It offers invaluable lessons for us today as we strive to preserve the remnants of wilderness. It's a powerful demonstration of how complexly and intimately intertwined climate, living ecosystems, and human activity are in the grand drama of life on Earth. Without a doubt, climate played a major role in the great extinction of the Ice Age giants. And while many theories place the primary blame on humans, it cannot be denied that the dramatic and global climate swings laid the foundation upon which the tragedy unfolded. They were either the primary driver of the extinction or the critical factor that sapped the strength of the megafauna, leaving them defenseless. The speed and scale of these changes presented ancient animals with a challenge that most simply couldn't cope with. Their bodies and habits, perfectly adapted to the stable, harsh conditions of the Ice Age, proved useless in the new, chaotic world. One of the first and most devastating blows was the loss of their home, their natural habitat. Let's fast forward to the last glacial maximum. Vast swathes of the northern hemisphere were then covered in a unique ecosystem that scientists call the Mammoth Steppe. It was a true paradise for giants, cold but incredibly fertile meadows where nutritious grains, sedges, and grasses grew in abundance. This world supported countless herds of woolly mammoths, woolly rhinoceroses, and mighty steppe bison. But then the planet began to warm. The ice caps that had encased the continents began to retreat and melt, and along with them, this lush steppe world began to disappear. Entirely new landscapes arose in its place. Dense, impenetrable forests advanced from the north, occupying formerly open spaces. Melting glaciers created gigantic swamps and marshes, while in other regions, conversely, drought set in, and deserts engulfed the once green lands. For animals whose entire lives were tied to cold, open plains, this was a catastrophe. Herds of herbivores suddenly found their world shrunk to a few scattered patches of land. This meant not only hunger and difficulty finding food during seasonal migrations. The isolation of small groups led to inbreeding, further weakening the populations. The sheer speed of these changes was a colossal stress. The warming at the end of the Ice Age was not a smooth and gradual process spread over thousands of years. No, it was a veritable climate fever, shaken by sharp temperature fluctuations. There would be sudden periods of warmth, like the Berling-Allerud interstadial. Then the world would plunge back into icy cold, as during the so-called Younger Dryas. These rapid changes, sometimes occurring in just a few decades, were a death sentence for large animals with their slow reproductive cycles. They simply couldn't adapt. Species perfectly adapted to stable cold suddenly found themselves in a world changing faster than they could evolve. This chaos, from cold to warm, from drought to wet and back again, created constant instability, making survival nearly impossible. Climate change dealt a direct blow to the most important thing: food. When the mammoth steppe disappeared, the nutritious grasses that formed the basis of the giant's diet gave way to plants that were either less tasty or simply lacked the necessary calories. Imagine, a dense forest cannot feed the same herd of bison as a vast pasture. These dietary changes caused severe nutritional stress. Animals became weaker, their immunity weakened, and they became easy prey for diseases and predators. Even for forest dwellers like mastodons, the changing forest composition could have meant starvation if their native tree species disappeared. Weakened organisms are an ideal target for disease. Groups of animals, exhausted by the loss of their homes and constant malnutrition, suffered from weakened immune systems. And sudden changes in temperature and humidity created ideal conditions for the spread of new viruses, parasites, and bacteria, to which megafauna had no defenses. Moreover, when animals were forced to huddle together on the last remaining patches of land, the risk of infection increased exponentially. High water levels also played a role. Melting glaciers caused a sharp rise in global sea levels. The water inundated vast coastal plains that had previously served as both pastures and vital migration routes. At times, the water raged in devastating torrents. Catastrophic floods, such as the infamous Lake Missoula outburst floods, literally razed the landscape, destroying vegetation and killing thousands of animals in their path, cutting their populations into isolated groups. Thus, while proponents of the extermination theory point the finger at humans, the climate hypothesis paints a different picture. It tells us that the giant populations were already on their last legs, exhausted and weakened by the most severe environmental pressures. Climate paved the way for the tragedy, creating vulnerable, cornered herds that became easy prey. Human intervention in these conditions was the final blow. Perhaps humans exacerbated the climate stress by burning forests or blocking the last migration routes. Either way, the end of the Ice Age ushered in an era of unprecedented environmental upheaval, and the clash of two titanic forces, a merciless climate and a new intelligent predator, humans, created a true cataclysm that led to the rapid and total extinction of megafauna. Now let's consider another, equally compelling theory. It posits that ancient human hunting played not just a significant, but in some cases a decisive role in the extinction of Ice Age giants. This concept is known as the overkill hypothesis, or overkill. Its essence is simple. As human tribes grew in number and spread across the planet, their hunting passion and efficiency became a death sentence for large animals. The pressure became so intense that giant populations began to decline and eventually disappeared completely. This pattern was particularly pronounced on the continents where humans arrived relatively late, North and South America. This hypothesis, like a detective story, rests on several key clues. First, there's the striking coincidence of timing. If we superimpose the migration routes of our ancestors on a world map and place a map of megafauna extinctions next to it, we'll see a near-perfect match. As soon as humans arrived in a region, the giants began to disappear shortly thereafter. In North America, this drama unfolded with lightning speed. Most large mammal species disappeared within a very narrow time window, just 1,000 to 2,000 years. This period coincides almost perfectly with the rise and spread of the so-called Clovis culture, approximately 13,500 years ago. This rapid extinction, often referred to as a prehistoric blitzkrieg, clearly hints at the emergence of a new, incredibly powerful and destructive factor in the ecosystem. The second clue is the naivety of the victims themselves. Imagine Africa or Eurasia. There, large animals lived side by side with human ancestors for hundreds of thousands, even millions of years. Over this vast period of time, they developed protective instincts. They learned to recognize these bipedal creatures as a mortal threat, to avoid them and to resist them. Their populations adapted to the constant hunting pressure. Now let's move on to America. When the first humans crossed the Bering Strait, they found themselves in a kind of lost world, a Garden of Eden, populated by giants who had never seen a human. Mammoths, mastodons, giant ground sloths, and ancient horses simply had no innate fear of this new, incredibly intelligent and armed predator. These unafraid, trusting populations were incredibly easy prey. They became the perfect target, which made them completely defenseless in the face of total extermination. The third factor, of course, was the astonishing effectiveness of hunting technologies. Imagine a world where survival depended not only on brute force, but also on ingenuity and technology. At first glance, ancient human tools seem incredibly primitive to us, merely sharpened pieces of stone. But in the hands of an experienced, battle-hardened hunter, working as part of a well-coordinated group, these simple tools turned into deadly weapons. A key breakthrough was the invention of throwing weapons, spears, which, with the help of special devices called spear throwers, flew farther, faster, and with greater force revolutionized hunting. Now, a person could deliver a fatal blow to a giant without getting close to its tusks, horns, and hooves, remaining at a safe distance. This greatly increased the chances of success and, more importantly, of returning home alive. But humans conquered not only by force, but also by cunning. They learned to control fire, turning it into a formidable ally. A wall of flame drove entire herds of animals, crazed with fear, straight into ambush, deep gorges, or the edge of a sheer cliff from which there was only one way, down to their death. Masterfully set traps and collective raids turned hunting into a true military operation. Archaeological finds provide irrefutable proof of this. All over the world, we find ancient human sites where the bones of mammoths, mastodons, and giant bison lie alongside stone tools. The calorific value of a single such carcass was colossal, enough to feed an entire tribe for weeks. It's no wonder that megafauna were such coveted prey. However, there was another invisible enemy that sapped the giant's strength: time itself. Megafauna lived and reproduced by its own rules. These enormous animals couldn't reproduce quickly. Their gestation periods lasted for months, producing only one, rarely two, young, which took years to mature and produce offspring of their own. Their populations grew painfully slowly, and when hunting pressure exceeded the natural rate of reproduction, even a seemingly insignificant number of animals killed could trigger an irreversible process. The population began to decline rapidly, and the species simply had no chance of recovery. It was precisely this biological characteristic, slow population growth, that made the Ice Age giants incredibly vulnerable. They were unable to adapt to the emergence of a new, intelligent, and ruthless predator. Unlike smaller, rapidly reproducing animals, they were unable to replace their losses. The hypothesis that humans were the cause of their demise is increasingly supported by the fossil record. We see several striking patterns. For example, extinctions primarily affected giant creatures, while smaller species suffered much less. Furthermore, the most catastrophic extinctions occurred on the continents where humans arrived most recently, the Americas and Australia. In Africa, our shared cradle, where animals evolved alongside humans for millions of years, such a collapse did not occur. But in Australia, where the first humans arrived about 65,000 years ago, an entire unique ecosystem disappeared. Giant kangaroos, tiger-sized marsupial lions, and enormous wombats, all of them vanished shortly after humans arrived. However, it would be too simplistic to blame our ancestors alone. Today, most scientists agree that the megafauna tragedy was caused by two devastating blows dealt simultaneously: ruthless hunting and abrupt climate change. On the one hand, nature itself rebelled against its giant children. Glaciers retreated, the climate changed, familiar pastures disappeared, giving way to forests, and drought gripped entire regions. All this weakened mammoth and rhinoceros populations, making them even easier prey for hunters. Climate change fragmented their vast habitats into tiny islands, trapping the animals in small areas where they were easier to track and destroy. This deadly cocktail of factors likely mixed in different proportions for each species and each region. Some species were more sensitive to climate change, others to human pressure, but the outcome was the same. Debate continues to this day, but one thing is clear: human hunters played a decisive role in shaping the world that emerged from the ruins of the Ice Age. It was one of the first and most terrifying examples of how our species can forever alter the biodiversity of the entire planet. When the gigantic ice sheets that covered entire continents began to retreat around 19,000 years ago, the world changed beyond recognition. By 10,000 BCE, this process was largely complete, revealing entirely new landscapes. Dense forests, endless grasslands, and vast wetlands replaced the lifeless, icy deserts. The planet was being reborn. One of the most dramatic changes was the advance of forests. Imagine, at the peak of the glaciation, most of the northern hemisphere was frozen solid. Boundless, treeless tundra and frigid steppes stretched for thousands of kilometers. Trees huddled only in small, isolated refuges somewhere in southern Europe. But then the climate began to warm. The first to reach the lands reclaimed from the ice were pioneer trees, easygoing birches and pines. Millennium after millennium, they moved north, followed by more demanding species: majestic oaks, elms, maples, spruces, and firs. Open, windswept expanses gave way to dense, dark forests. This transformation altered not only the appearance of the continents, but also the planet's ecology, creating new habitats for thousands of animal species. Along with the forests, new grasslands emerged, completely unlike those that had existed during the Ice Age. Where ice or permafrost had once lain, lush temperate steppes and prairies now sprawled. These new grasslands became home to new communities of herbivores. In North America, for example, the Great Plains became a vast green ocean capable of supporting millions of bison herds. It was a world strikingly different from the cold, dry steppes where mammoths had once grazed. But the most astonishing spectacle was the birth of new water worlds. Melting glaciers released truly colossal volumes of water. This water filled the depressions and basins left by the glaciers, forming countless new rivers and lakes. Their size staggered the imagination, from small but deep lakes formed in the place of melted ice flows to gigantic periglacial seas. Such was Lake Agassiz in North America, whose surface area exceeded all of today's Great Lakes combined. Many of these bodies of water were temporary, but others remain to this day. Tens of thousands of lakes in Canada, Scandinavia, and the northern United States are a direct legacy of the melted glaciers. Along with the lakes, vast wetlands also emerged. Meltwater saturated the soil, creating ideal conditions for moisture-loving vegetation. In lowlands where the water could not find drainage, gigantic swamps and marshes formed. Melting permafrost lying beneath the surface created an impermeable layer that prevented water from seeping deeper, contributing to swamping. These new ecosystems became home to a huge diversity of life and began to play a key role in the global cycle of matter. The very Earth itself underwent incredible changes. Freed from the unimaginable weight of a kilometers-thick ice cap, the Earth's crust began to slowly rise. This process, known as isostatic uplift, continues even today. It altered the topography, riverbeds, and coastlines. Meltwater flows and advancing glaciers transported vast quantities of sand, clay, and boulders, forming entirely new soil types, many of which proved incredibly fertile. As a result, a completely new mosaic of landscapes emerged on the planet. The transition from a world of ice and cold stepped to a world of forests, grasslands, and countless freshwater bodies created new opportunities for life. This global environmental restructuring directly influenced the evolution and distribution of plants and animals, but it also forced human change. As giant beasts disappeared and landscapes were transformed, people were forced to adapt. Specialized hunting of megafauna gave way to more diverse means of survival based on exploiting all the riches offered by the new, reborn world. Imagine a world awakening from a long, icy slumber. Landscapes born from the retreating glaciers became the cradle of modern ecosystems and, ultimately, human civilization. But at the heart of these changes was water. The Great Melt, the end of the Ice Age, triggered a colossal, fundamental restructuring of river systems across the planet, especially in lands that had recently been locked in kilometers of ice. Incredible torrents of meltwater, coupled with relentless erosion and the movement of glacial sediment, forged entirely new river routes that paved the way for future human development. During this turbulent era, valleys changed their appearance beyond recognition, and the very hydrological systems that shape our planet to this day were formed. It was a time of unbridled water. Before the ice began to move, rivers flowed along long-established channels carved according to ancient pre-glacial topography. But the advance of giant glaciers disrupted this order, redrawing the map of the world. Glaciers acted as impassable dams, blocking existing river valleys, forcing streams to find new routes, and sometimes burying entire drainage systems. Take North America, for example, or the advance of the Laurentide ice sheet forced rivers to turn north, literally pinning them at the very edge of the advancing ice. This led to the creation of enormous proglacial lakes, which, overflowing, overflowed their banks and carved out new, previously unseen channels. When the ice sheets began to retreat, an incredible amount of meltwater was released. This water rushed from the ice fronts in gigantic torrents, forming powerful, winding rivers that rushed across the newly born land. These meltwater streams weren't just numerous, they possessed monstrous force, many times greater in size and power than modern rivers flowing through the same regions today. They dragged with them countless quantities of sand, gravel, and giant boulders, which were then deposited on the plains left behind by the retreating ice. The volume and speed of these water masses were so great that they wielded colossal destructive force. They literally tore into bedrock, deepening existing valleys or creating entirely new ones from scratch. Consider the impressive gorges and canyons in many regions once covered by glaciers. These are the scars on the planet left by erosion caused by meltwater. One of the most dramatic consequences of these events was the formation of new watersheds and the so-called capture of river systems. As the ice sheets retreated, new lowlands and drainage routes opened up. Rivers previously icebound could find new, shorter, and more direct routes, abandoning their old channels forever. This process, which scientists call stream capture, led to dramatic changes in the size and flow of entire river basins. Take, for example, the modern Ohio River in North America. Its course is a direct result of the Ice Age. It became the main channel through which meltwater from the retreating Laurentia ice sheet rushed toward the ocean. Similarly, the inexorable melting of glaciers forever altered the course of the mighty Missouri River. The Great Lakes system in North America is perhaps the most striking example of how melting ice can sculpt entire continents. The basins of the Great Lakes themselves were carved by the crushing force of the Laurentide ice sheet. As the ice retreated, these gigantic depressions filled with meltwater, creating a series of proglacial lakes that eventually became the Great Lakes we know today. The connections between these lakes shifted repeatedly as the land, freed from the glacial pressure, slowly rose. This created temporary waterways and connections, marking different stages of lake formation and massive water discharge processes. In Europe, the melting of the Scandinavian ice sheet caused equally dramatic changes to river systems. Consider the Baltic Sea. It has gone through several remarkable stages of development. Initially, it was a gigantic freshwater lake known as the Baltic Ice Lake, which periodically emptied catastrophically. Only later, when it established a connection with the ocean, did it transform into the brackish sea we see today. The rivers flowing into the Baltic region were profoundly impacted by these processes. Groundwater levels fluctuated constantly, and glaciers reshaped their fates. The consequences of those massive river transformations are still imprinted on the landscape. Many modern rivers flow through valleys created or radically altered by the glacier and its meltwater. Terraces along riverbanks, formed from glacial deposits, serve as silent witnesses to higher water levels in the past, when meltwater torrents rushed at breakneck speed. The distribution of sand and gravel along riverbeds is further evidence of the incredibly intense water flow during the Great Melt. But these changes were more than just geological oddities. they had enormous, fateful consequences for the entire environment. These were truly astonishing transformations. They had a colossal impact on ecosystems and, of course, on the lives of early humans. The emergence of new rivers opened up access to fresh water, created new fishing opportunities, and paved new migration routes for animals and people. But on the other hand, these same rivers also posed a deadly threat: massive floods and constant channel shifts, which required incredible adaptability from ancient humans. The transformation of river systems at the end of the Ice Age was a rapid and stunning demonstration of the Earth's ability to adapt to global climate shifts. The melting of massive ice sheets led to dramatic changes in the Earth's hydrology. This process created new freshwater bodies, most notably vast, gigantic lakes. These lakes varied greatly in composition, size, longevity, and origin, but they all had one thing in common. They were created by unimaginable volumes of meltwater released from decaying glaciers. The birth of these lakes forever altered landscapes and impacted the lives of all living things. The climate changed, creating entirely new ecological niches. One of the most impressive types of lakes resulting from this process were the so-called periglacial lakes. These were enormous bodies of water that formed at the very edges of retreating ice sheets. Often, their shores were formed by the glacier itself or by glacial moraines, giant banks of rock debris left behind by the ice. A striking example of such a monster is Glacial Lake Agassiz in North America. This colossal lake sprawled across the very center of the continent as the Laurentia ice sheet began to melt and retreat northward. At its peak, Lake Agassiz was so vast that it easily dwarfed all of the modern Great Lakes combined. It was a true inland sea, inundating vast swaths of the modern-day Canadian provinces of Manitoba, Saskatchewan, and Ontario, as well as the U.S. states of North Dakota and Minnesota. It contained approximately 18,000 cubic kilometers of water. The lake no longer exists, but in the past it periodically breached its natural dams, releasing enormous torrents of fresh water through various outlets. These breaches were sometimes catastrophic, and, according to scientists, significantly impacted global ocean circulation. Another famous proglacial lake was Glacial Lake Missoula, formed by a protrusion of the Cordilleran ice sheet in western Montana. This lake's fate was even more dramatic. It was repeatedly dammed by ice, filled to the brim, and then the dam burst. The lake then catastrophically drained in a series of apocalyptic floods that literally washed away everything in their path. These floods created the bizarre, ravaged landscape of eastern Washington state known as the Channeled Scablands. Over millennia, these events created a unique landscape of dried-up Niagara-sized waterfalls and deep canyons carved into the rock. The emergence and disappearance of such gigantic lakes played a decisive role in the distribution of water and sediments across entire continents. In addition to these colossal behemoths, countless other, smaller periglacial lakes formed in regions that experienced glaciation. In Europe, in the basin of what is now the Baltic Sea, the Baltic Ice Lake formed. It emerged when the Scandinavian ice sheet retreated. This lake went through several stages in its development, at times connecting with the ocean and at other times breaking through due to ice movement or land uplift, before finally becoming the salty Baltic Sea we know today. These periglacial lakes were key elements of the landscape as it was being cleared of ice. They served as temporary reservoirs for glacial meltwater and even influenced the regional climate, significantly reducing temperatures. Another, very common type of glacial lake existed, so-called kettle lakes. These relatively small, often perfectly circular bodies of water form when giant chunks of dead ice, carved from a retreating glacier, become buried in glacial sediment. As these buried ice blocks slowly melt, they leave behind deep depressions in the landscape, which then fill with water. Kettle lakes are abundant in regions once covered by glaciers, such as Wisconsin and Minnesota in the United States, as well as in many parts of Canada and Northern Europe. Their sheer number testifies to the chaotic and uneven melting of the ice sheets. Finger lakes are another distinctive type of glacial lake, particularly prominent in places like upstate New York. These long, narrow, and incredibly deep lakes typically form in pre-existing river valleys that were significantly deepened and straightened by the crushing, erosive force of advancing glaciers. As the ice retreated, these ultra-deep valleys filled with meltwater, creating the lake's distinctive, elongated, finger-like shapes. Tarns, also known as cirques, are small, often round lakes that, let's take a trip to a world locked in ice. Contrary to popular belief, the Great Ice Age was a time not only of bitter cold, but also of total drought in many parts of the planet. Imagine, the enormous volumes of water that fill the oceans today were literally locked away in colossal glaciers, several kilometers thick. These ice caps, covering entire continents, acted like giant freezers, extracting moisture from the global circulation. As a result, there was much less water vapor left in the atmosphere, meaning rain became rare. This led to vast territories being transformed into deserts and semi-desert steppes. The lands that today are the fertile plains of North America and Eurasia were, in those distant times, parched and lifeless expanses. Vegetation here was sparse, and in some places completely absent, giving way to barren landscapes. Moreover, massive and stable high-pressure zones formed above the giant ice sheets. This cold air displaced the usual storm fronts and rain clouds closer to the equator. This created a paradox. Regions known today for their humid climates could suffer from drought during the Ice Age. Conversely, some modern deserts received more moisture during the Ice Age. A striking example is the southwestern United States, where the shifting climate zones created enormous freshwater lakes that no longer exist today. Another inseparable feature of that world were fierce, incessant winds. Their origin lay in the colossal temperature difference between the icy continents and the relatively warm ocean waters. Powerful high-pressure systems above the glaciers created a gigantic difference, generating constant, hurricane-force air currents that swept across the entire planet. These winds weren't just a weather phenomenon, they were true landscape sculptors. They picked up billions of tons of fine dust, known as loess, from the glacial wastelands and transported it thousands of kilometers. As these deposits settled, they formed entire layers of fertile soil. In some regions, such as China or the central United States, these loess layers are tens, even hundreds of meters thick. It is on these ancient deposits that the world's most productive agricultural lands now lie. But the winds also had a dark side. They transformed an already frigid world into a veritable icy hell. Bone-chilling winds and ferocious blizzards made life beyond the glaciers almost unbearable. The combination of frost and wind created what's known as a periglacial environment, where permafrost reigned. The soil here froze many meters deep and didn't thaw for years, even decades. This process created unique landforms, for example, patterned earth, where rocks, driven by freeze-thaw cycles, formed into bizarre geometric shapes. The Ice Age world was full of astonishing icy wonders, from giant ice wedges in the ground to pingos, enormous mounds with an ice core inside. The climate was harsh, endless, dark, and frosty winters gave way to short, cool summers. Any living creature that dared to brave this era fought a daily battle for survival. The combination of cold, dryness, and merciless winds created a world full of dangers and hardships. In this harsh world, an eternal drama of life and death unfolded. The Ice Age ecosystem was a veritable arena where giant herbivores acted as living fortresses, hunted by predators who had honed their skills to perfection. This complex food chain was forged in the crucible of the Ice Age, giving rise to unique strategies of attack and defense. And since the prey reached truly cyclopean proportions, the hunters had to be equal. Among the most formidable inhabitants of those times, it wasn't only the predators that stood out. Giant ground sloths, despite their apparent clumsiness, were capable of surprisingly fast and agile sprints, and their powerful claws made them deadly opponents. Jaguars, whose grace and speed still inspire admiration, were masters of surprise ambush attacks. Each of these animals fought for its place under the cold sun, using the unique talents bestowed by evolution. But the king of this arena was undoubtedly the saber-toothed cat, Smilodon fatalis, which reigned supreme in North America. These magnificent predators were renowned for their incredible fangs, resembling two curved daggers which could grow up to 18 centimeters, 7 inches. Despite their name, saber-toothed cats were not direct ancestors of modern cats, but belonged to an entirely separate, now extinct lineage. Their build was incredibly powerful and muscular, more reminiscent of a modern bear than a lion or leopard. This suggests that they were not runners, but masters of ambush. Their powerful forepaws were designed to grab and pin even the largest prey, and then came their main weapon. Their long fangs were likely used for a single, precise and fatal bite to the victim's throat. This wasn't a brutal tear of flesh, but a surgically precise thrust aimed at the jugular vein or trachea, causing rapid blood loss and shock. Moreover, the fangs themselves were quite fragile and unsuitable for gnawing bones or fighting a struggling prey. Therefore, Smilodon had to first completely immobilize its prey with the force of its body before delivering the fatal blow. Its targets were slow-moving giants, mammoths, mastodons, ground sloths, and ancient bison. Astonishing discoveries in the La Brea tar pits, where the remains of thousands of animals have been preserved, indicate that Smilodon may have lived in prides. The discovery of multiple individuals of different ages in one place suggests that they may have hunted together, as taking down a mammoth alone would have been an almost impossible task. A completely different tactic was employed by other rulers of the glacial plains, the dire wolves, Canis dirus. These beasts were noticeably larger and more massive than their modern grey counterparts, weighing up to 70 kilograms. Their powerful jaws and teeth were ideally suited for crushing bones, making them not only effective hunters, but also excellent scavengers, capable of consuming a carcass completely. Dire wolves were social predators that relied on the strength of their packs. This strategy allowed them to hunt very large prey. Their diet included bison, wild horses, camels, and even young mammoths or mastodons. Unlike saber-toothed cats, which operated from ambush, wolves were tireless pursuers. They could chase their prey for hours, exhausting it and attacking with coordinated lunges. Their social structure likely resembled modern wolf packs, with a clear hierarchy, complex communication systems, and well-coordinated teamwork. Another apex predator was the cave lion, Panthera spelaea. It was one of the largest cats to ever roam the earth, surpassing even modern African lions in size. It inhabited the vast expanses of Eurasia and North America. It got its name not because it lived in caves permanently, but because it often used them as temporary shelters or dens for breeding. These animals combined incredible strength and agility. Their prey included large and medium-sized herbivores, reindeer, horses, bison, and young mammoths. Scientists still debate their social behavior. Perhaps they lived in small groups, or perhaps they were more solitary than their modern African relatives. Their hunting strategy in cold climates relied on stealth and a single, powerful, decisive lunge, relying on their colossal physical strength. The cave bears, Ursus spelaeus, are also worth mentioning. These giants reached sizes comparable to modern polar bears. However, judging by the structure of their teeth, they were primarily vegetarian, feeding on plants, berries, and roots. Nevertheless, they were omnivorous and highly adaptive animals, never missing an opportunity to scavenge. Although they were not active hunters of large game, these powerful creatures were true warriors, capable of fending for themselves and defending their territory from any predator. Their main role in the ecosystem was to process enormous amounts of plant matter and clear the area of carrion. They spent most of the winter hibernating in deep caves, which gave them their famous name. Among other formidable predators of that era, the short-faced bear Arctidus of North America stood out, an incredibly fast and powerful heavyweight sprinter that could both actively hunt and snatch prey from other predators. Spotted hyenas and even crocodiles also expanded their reach across Eurasia, serving as hunters and chief sanitation workers during the Ice Age, scavenging the remains of other giants' feasts. These courageous hunters faced incredibly difficult challenges. In extreme cold, any hunt required colossal energy expenditure, and prey was either rare or scattered across vast territories. Moreover, the prey itself was deadly, capable of inflicting fatal injuries on an attacker with a single blow of a hoof or tusk. It was a never-ending evolutionary arms race. Prey evolved their own defenses: thick hide, gigantic size, powerful limbs for defense, and herd behavior to confuse predators. In response, predators honed their weapons. Saber-toothed fangs grew longer, and pack hunting became increasingly coordinated. And now, a new, most dangerous predator has entered this arena: humans, a member of the species Homo sapiens. During the late Ice Age, ancient hunters developed complex and deadly techniques. They used spears with stone tips, spear throwers that allowed them to strike targets from a distance, and ingenious traps. Their main weapons were intelligence and the ability to hunt in large, coordinated groups. Imagine a world emerging from the grip of permafrost. Here, high in the mountains, a magnificent spectacle unfolds: the birth of new lakes. Look at these colossal bowls, these natural amphitheaters, mercilessly carved out of rock by the movement of gigantic glaciers. And now, as the era of cold draws to an end, the ice titans begin to retreat. Meltwater, pure and cold, rushes down, filling these depressions to the brim and giving life to countless new bodies of water. At the end of the Great Ice Age, this event became a true catalyst for change for the entire planet. These newborn lakes became oases, vast sources of fresh water that breathed life into devastated landscapes. They became the cradle of new ecosystems. Their transparent depths gave birth to a diversity of fish, amphibians, and countless invertebrates previously unknown in these places. Moreover, these watery surfaces became crucial landmarks and resting places along the celestial highways of migratory birds. For the ancient people who inhabited this changing world, lakes were a true gift. They were a source of inexhaustible resources: fish, drinking water, and life itself. This fundamentally changed the distribution patterns of our ancestors and their survival strategies. But the value of these lakes extends far beyond their mere resource. The sediments that accumulated at their bottoms over centuries are now priceless archives of the past. Like time capsules, they preserve the pollen of ancient plants, the remains of microscopic organisms, and other evidence that allows scientists to decipher the history of climate change and the evolution of our planet. The very process of their formation was inextricably linked to deep geological forces and gigantic movements of the Earth's crust. Imagine the weight of a kilometer-thick ice cap pressing down on the continents. As this incredible weight disappeared, the land began to slowly, over millennia, rise as if straightening its shoulders. This process, known as isotropic recoil, continued to shape the landscape. Sometimes this uplift caused lakes to tilt, their waters to find new channels, or even disappear entirely. In other cases, uneven crustal uplift created entirely new basins that immediately filled with water. Thus, the birth of these lakes was a dynamic, captivating process, influenced by both the rapid melting of the ice and the slow but inexorable forces of geology. We see the legacy of that era today in thousands of lakes scattered across the northern hemisphere. They serve as a lasting reminder of the dramatic metamorphoses the Earth experienced in its icy past. When the planet's icy shell began to crack and retreat, humanity found itself at a crossroads. The familiar world was disappearing, and to survive, change was necessary. A long and difficult period of adaptation began. A survival strategy based solely on hunting the giants of the cold steppes no longer worked. The time had come to seek new, more diverse sources of food. This turning point in history, known in Europe as the Mesolithic and in America as the Archaic period, forced people to invent new tools, new technologies, and even new social structures to avoid being wiped off the face of a changing Earth. One of the key challenges was the abandonment of megafauna hunting. At the peak of the Ice Age, entire cultures, such as the famous Clovis people in North America or Upper Paleolithic hunters in Eurasia, built their lives around the hunt for true colossi. Their targets were mammoths, mastodons, woolly rhinoceroses, and giant bison, living mountains of meat, fat, and bone. These animals provided everything: abundant food, warm hides for clothing and shelter, and strong bones for tool-making. But with global warming and the disappearance of familiar pastures, the Age of Giants came to an end. Many of these species became extinct, leaving humans facing starvation. People were forced to radically revise their diet and hunting tactics. Their diet included smaller, more agile animals: swift deer, elk, wary wild boar, as well as all sorts of rodents and birds. Hunting such game required a completely different approach. Heavy spears, effective against the lumbering mammoth, proved useless. They were replaced by lighter, more maneuverable javelins, spears, and a brilliant invention, the spear thrower, or atlatl, which allowed for striking a target with incredible force and over a long distance. The pinnacle of this technological advancement was the bow and arrow, a weapon requiring precision and skill. Other methods also changed. People began to actively use traps and snares for small game. What had been ineffective against giants proved incredibly effective in the New World. The new era was an era of water. Melting glaciers gave the world countless rivers, lakes, and new coastal zones. Humans quickly turned their attention to the waters, which concealed untold riches. Fishing transformed from a casual pursuit into a pillar of survival. This led to the creation of a whole arsenal of specialized tools: bonefish hooks, braided nets, and barbed harpoons for hunting large fish. In coastal areas, people discovered another reliable food source: shellfish. Archaeological excavations from that time reveal gigantic mounds of discarded shells, silent monuments to thousands of feasts on the shores of the ancient sea. These mountains of shells speak eloquently of the importance of this resource. Stable food sources near water allowed people to lead a more sedentary lifestyle. They no longer had to constantly follow migrating herds. Groups could remain in one place for much longer without risking depletion of food supplies. This was a striking contrast to the constant pursuit of megafauna by hunters, but survival depended on more than just what they could catch and spear. Early humans were rediscovering the earth beneath their feet. Foraging for plants became much more important. As temperatures warmed and humidity increased, dense forests emerged where the tundra steppes had been, giving humans access to a vast variety of edible plants. People learned to find and use the earth's hidden treasures: nutritious roots and tubers, juicy berries, and calorie-rich nuts and seeds. This required new knowledge about the seasons, plant growth cycles, and methods of processing them. New tools came into use: stones for grinding grains and nuts, wicker baskets for harvesting. A plant-based diet reduced the dangerous dependence on hunting luck and provided a more stable and balanced diet. These revolutionary changes in lifestyle inevitably brought with them social transformations. While small, highly mobile hunting bands were the norm during the Ice Age, now, with the advent of abundant and diverse resources, more stable communities began to form. Semi-permanent or seasonal base camps emerged, becoming vibrant centers of life. During periods of plenty, such as the salmon runs or nut harvests, large groups of people could gather in such camps. Then, in leaner times, they could disperse into smaller family units. Archaeologists find evidence of the construction of increasingly larger and more complex settlements, suggesting a gradual transition to sedentarism. This, in turn, facilitated the development of more complex social structures, increased population density in fertile areas, and possibly the emergence of the first trade networks for the exchange of raw materials and finished goods. The need to adapt to new realities became a powerful driver of technological progress. In addition to improved hunting and fishing tools, people invented numerous devices for processing plant foods and tanning hides. New types of clothing, more suitable for warmer climates, and diverse types of housing emerged. But one of the most significant technological breakthroughs of that era was the improvement of microlithic technology. Imagine tiny stone inlays, perfectly shaped. Like building blocks, they were used to create composite tools. These miniature blades were used to make serrated spearheads, arrowheads, and even sickles for harvesting wild grains. These small but incredibly versatile tools were extremely efficient and economical in terms of the consumption of valuable raw materials. Thus, the end of the Ice Age was not just a climate change, but a true revolution in human life. The transformation of landscapes and wildlife forced our ancestors to demonstrate marvels of ingenuity and adaptability. This period, which we call the Mesolithic in the Old World and the Archaic period in the New, was marked by a remarkable technological advancement that went far beyond the conventional notions of the Stone Age. At the center of this technological revolution was the widespread use and refinement of microliths. These were tiny stone blades, fashioned into precise geometric shapes, triangles, crescents, or trapezoids. Typically, they were no more than 2 to 3 centimeters in size. The key was that these tiny flakes weren't used individually. They served as components for creating more complex composite tools. They were inserted into specially cut grooves on bone, horn, or wood bases, creating a single hole. This ingenious technology created incredibly sharp, serrated spear and arrowheads that inflicted terrible wounds. They were also used to create cutting edges for knives and sickles. The main advantage of microliths was their incredible efficiency. Dozens of sharp blades could be crafted from a single small piece of high-quality stone, called a core, making production very cost-effective. It was an ingenious modular system of the Stone Age. If one of the microliths in a tool broke, it could be easily removed and replaced with a new one without having to discard the entire tool. Let's move on to a world just emerging from the grip of the glaciers. Here, at the dawn of a new era, the technologies of our ancestors reflected their desperate desire for survival, forcing them to create increasingly specialized and meticulously designed toolkits. Now that the vast glaciers had retreated, people's gaze increasingly turned to water. Rivers and lakes brimming with life, this new passion for fishing gave birth to a whole arsenal of tools created specifically for the development of aquatic resources. Imagine an ancient fisherman on the riverbank. In his hands is not just a sharpened stick, but a skillfully crafted fishhook made of bone, strong deer antler, or even hard shell. These tools became commonplace, and their sophisticated design allowed them to fish from the dark depths with incredible efficiency. But hunting larger prey required something more formidable. This is where harpoons came into play. They were made from the same materials, bone or horn, but often equipped with serrated, deadly tips. Such weapons could kill not only giant fish, but also marine mammals. Every such find at ancient sites is direct evidence of how heavily our ancestors relied on aquatic sources of protein. Of course, the most ingenious traps of that time, fishing nets, rarely survive in their original form, but we find irrefutable evidence of their existence. Look at these stones with carefully drilled holes. They're weights that pulled the net to the bottom. And here are the thin bone or horn needles, the ideal tool for weaving and mending these nets. The emergence of such an integrated approach to fishing was a true revolution. The ability to stockpile vast quantities of fish during the seasonal spawning season allowed people, for the first time, to abandon their perpetual migrations and establish permanent settlements along full-flowing rivers and on the seashore. At the same time, tools for working with the bounty of the land were also improving. Forests were advancing, bringing with them an incredible diversity of plant foods. People learned to gather a wide variety of seeds, nuts, and roots, but how to extract value from them? Grinding stones, massive slabs, and convenient handheld millstones were invented for this purpose. With their help, wild grains, hard nuts, and other plant products were ground into nutritious flour or paste. These seemingly simple tools bear witness to a crucial shift in the ancient human diet, which became increasingly rich in plant carbohydrates. To extract nutritious roots and tubers from the ground, primitive but effective digging sticks were most likely used. Sometimes they were even weighted with specially crafted stones for greater efficiency. Unfortunately, wood is a fragile material, and time has mercilessly worn away these artifacts, making them extremely rare for archaeologists to find. The same fate befell woven baskets and vessels. They were absolutely essential for transporting the harvested crop, but only indirect evidence of their existence has survived to this day. The changing climate forced a rethinking of hunting practices. The world had changed. The Ice Age giants, hunted for generations, died out one after another. They were replaced by new masters of the forests, smaller, faster, and more agile animals, deer, elk, and wild boar. Hunting them required entirely different weapons. The bow and arrow were the perfect answer to this challenge. It was a ghost weapon. It possessed colossal advantages over heavy spears. It had a longer range, was more accurate, and was much more convenient in dense forest cover. Hunters could strike wary prey from a safe distance, remaining undetected. This technological adaptation gave rise to a whole variety of specialized arrowheads, often crafted from tiny but razor-sharp stone flakes called microliths. At the same time, tools for everyday needs continued to develop. As humans spread across the planet and explored new climates, the need for high-quality, functional clothing continued. Bone and bone needles became ever thinner and more elegant. This allowed for much more precise stitching of hides, creating clothing that fit perfectly. Such clothing could provide both better protection from the cold and necessary ventilation in the heat. As before, scrapers were indispensable for processing hides, and any sharp implement, whether made of stone or bone, was used to puncture thick leather. But humans didn't live by mere survival. This era witnessed a true flourishing of symbolism and art. Specialized engraving tools called burins appeared, used to carve complex, intricate patterns onto bones, antlers, and even stones. These works could have been both wearable art objects and perhaps the first counting or recording systems. We also find numerous personal adornments, beads and pendants made from a wide variety of materials. Their creation required a whole range of tools for drilling, polishing, and shaping these exquisite decorative objects. So what conclusion can we draw from this kaleidoscope of ancient technologies? The trend was clear: a race for efficiency, a striving for versatility, and the emergence of specialization. Each tool was created to solve a specific problem, and precious raw materials were used ever more economically and rationally. These technological breakthroughs were no accident. They were a direct response to the challenges of a changing world. It was precisely this adaptability that allowed humans not only to survive, but to thrive in a new reality, one that no longer accommodated the giants of the Ice Age. Thus, the foundation was laid for the future Great Revolution, the transition to agriculture and sedentary life. The incredible ingenuity displayed in the creation of these new tools serves as the clearest testimony to the mental flexibility and ability of our distant ancestors to adapt and solve any, even the most complex problems life presented them with. These ancient hunters relied on more than brute force. Their main weapons were their keen intellect and the ability to work together. Imagine a group acting as a single organism, using nature itself as an ally. They masterfully drove enormous animals into natural traps, deep ravines or swamps, or staged deadly raids, throwing prey from high cliffs. This ability to plan intricately and manipulate the environment gave them a decisive advantage for survival in the icy hell of the Pleistocene. The ability to communicate and create increasingly sophisticated tools allowed humans to challenge even the most colossal giants of the era. And herein lies one of the greatest dramas of paleontology. What was the role of humans in the great extinction that wiped out the megafauna at the end of the Ice Age? The debate continues to this day. But one thing is certain. Humans emerged as a formidable force, a new apex predator at the top of the food chain. They began to directly compete with saber-toothed tigers and cave lions, often emerging victorious in this merciless struggle for resources. This fragile and constantly shifting balance between hunters and their prey was the hallmark of the Ice Age world, a world where survival depended on primal strength and indomitable instincts. When we hear the phrase ancient forests, our imaginations typically conjure up images of dense, warm, and vibrant jungles like those in Jurassic Park. But the Ice Age world was completely different. Vegetation there obeyed the dictates of the cold. The icy climate gave rise to unique natural zones, biomes, where only the most hardy and frost-adapted species dominated. The main landscapes of the planet during that era were endless tundra, harsh taiga, and vast, cold steppes, which scientists call mammoth prairies. It was these plant communities that served as the foundation upon which the astonishing animal life of that time rested. At the leading edge of the icy world, at the very edges of giant glaciers, and at high latitudes, lay the tundra. This was a land where trees dared not grow. Permafrost, gripping the soil like an icy grip to an enormous depth, prevented roots from penetrating. Only during the short, cool summer did the topsoil thaw, giving low-growing plants a chance to thrive. The tundra kingdom was a world of mosses, lichens, sedges, grasses, and dwarf shrubs, such as the polar willow. Here, in these extreme conditions, unique life forms flourished, such as dwarf willows and birches. They developed astonishing survival strategies. Their low, prostrate habit allowed them to escape the icy winds and find shelter under a protective blanket of snow. Moreover, their life cycle was incredibly short, allowing them to flower and produce seeds in the short time afforded by the Arctic summer. Their shallow root system was not a whim, but a necessity. Penetrating the perpetual ice was impossible. And although at first glance the tundra might appear to be a lifeless desert, it was in fact a vital food source for a multitude of animals. This ecosystem served as a primary food source for reindeer, mighty musk oxen, and tiny lemmings, herbivores perfectly adapted to life in the cold. The tundra was a surprisingly resilient ecosystem, capable of supporting a remarkable diversity of life in a world bound by ice. Further south, where the climate's icy grip loosened somewhat, the boreal forest, better known to us as the taiga, began. This biome was the realm of coniferous trees, which had perfected the art of surviving the cold. Various species of spruce, fir, pine, and larch dominated here. Every detail of these trees was designed to combat frost. Their needle-like leaves minimized the loss of precious moisture, and their waxy coating served as a veritable armor, protecting them from freezing. The perfectly conical shape of their crowns allowed heavy snow to slide easily without breaking branches under its weight. These taiga forests provided vital shelter and food for many animals, forming a kind of buffer zone between the open tundra and warmer regions. Of course, they weren't as vast as today's Siberian forests, but patches of taiga existed wherever conditions were even slightly milder, for example, in wind-sheltered valleys or on low slopes. But perhaps the most grandiose and widespread ecosystem of the Ice Age was the cold grasslands, often called the Mammoth Steppe. Imagine a vast treeless ocean of grasses that covered vast swathes of Eurasia and North America. Today, these lands are covered by forests or deserts, but during the age of mammoths, a surprisingly fertile and diverse ecosystem flourished here. This sea of grass was dominated by various grasses, sedges, and a variety of flowering herbs. Unlike modern grasslands, the plants of the Mammoth Steppe were perfectly adapted to the cold, dry climate and frozen soil. The incredible productivity of these grasslands, even in the perpetual cold, was key to supporting colossal populations of giant herbivores. Herds of woolly mammoths, steppe bison, wild horses, and woolly rhinoceroses grazed here. These animals, in turn, shaped their own world. By constantly eating and trampling the grass, they prevented trees and shrubs from sprouting, maintaining the existence of the steppe. It was a symbiosis on a planetary scale. The mammoth steppe was a unique ecosystem, unlike anything we see on Earth today. Its disappearance at the end of the Ice Age directly coincided with the extinction of the giant animals whose lives depended entirely on it. In more localized areas, such as river valleys, where there was more moisture and warmth, other types of vegetation could have survived. So-called gallery forests grew there, with patches of deciduous trees that served as refuge for species less adapted to the open cold. All these vegetation zones were incredibly dynamic, shifting north and south like living beings, following the movement of glaciers and responding to the slightest changes in global temperature. How were scientists able to peer into this lost world? The answer lies in the microscopic evidence nature has preserved for us. Paleobotanists' primary tool is pollen analysis. By studying fossilized pollen, preserved for millions of years in lake sediments, peat bogs, and ice cores, scientists can reconstruct the vegetation of the past with astonishing accuracy. They literally read the history of which plant species grew in a given region. Another type of evidence is macroscopic fossils, perfectly preserved leaves, seeds, and even fragments of wood. But most astonishing is the analysis of the stomach contents of herbivores whose carcasses were found in permafrost. Their last meal gives us a direct insight into their diet. All these threads of evidence weave together to create a coherent picture of a world where plant life, though unlike our own, was incredibly rich and created a complex ecosystem that supported everything from the tiniest insects to giant mammoths. It was the unique characteristics of these ancient plants that were key to the prosperity of the entire Ice Age world. But the Ice Age isn't just a time of giant beasts and endless glaciers. It's also a crucial chapter in human history. This harsh era became a cradle for early human groups who not only survived in unimaginable conditions, but thrived in them. At that time, two distinct human species existed on the planet: Neanderthals and our direct ancestors, the early modern humans known as Cro-Magnons. Their lives offer a striking example of human ingenuity, resilience, and the will to survive in the face of perpetual cold and resource scarcity. Neanderthals, members of the species Homo neanderthalensis, were the true masters of glacial Eurasia. Their domain stretched from Western Europe to Central Asia and the Middle East. This extinct human species appeared around 400,000 years ago and disappeared approximately 40,000 years ago, having already witnessed the arrival of our ancestors in Europe. Neanderthals possessed an incredibly robust physique, far more powerful than that of modern humans. They had shorter, stockier limbs, a broad chest, and rippling muscles. Every detail of their body was a true machine for surviving the cold. This is a perfect example of Bergmann's rule, which states that in cold climates, a massive body is an advantage because it retains heat better. Neanderthal skulls were elongated, with powerful brow ridges and a very large nose, which likely served as a kind of radiator, warming and humidifying the icy air before it entered the lungs. Their brains were, on average, even slightly larger than ours, although their internal organization may have been different. Neanderthals were unrivaled hunters who specialized in the largest and most dangerous game: woolly mammoths, rhinoceroses, bison, and reindeer. Their tactics were not based on long-distance pursuit, but on deadly close-quarters combat. They relied on their colossal strength and heavy spears, which they used to strike at close range. This was an incredibly risky hunting method. Studies of their skeletons confirm this. Numerous healed bone fractures eloquently testify to injuries sustained in fierce battles with giants. Neanderthals lived in small, mobile groups, finding shelter in caves and rock grottos, or building temporary shelters in the open. Their diet was primarily meat-based, but they were also not averse to foraging, eating plants, fruits, and nuts whenever possible. But behind this rugged exterior lurked something more. There is evidence that Neanderthals cared for sick and wounded tribesmen and performed ritual burials for the dead. These are glimmers of compassion and symbolic thought, a spark of humanity in a harsh, icy world. Their culture, imprinted in enigmatic stone tools, was undoubtedly effective, but it lacked the diversity and sophistication that later humans excelled. However, they mastered fire. This primordial gift was absolutely essential for keeping warm on icy nights, cooking food, and warding off predators lurking in the darkness. Meanwhile, in Africa, around 300,000 years ago, entirely new players emerged on the world stage, early modern humans whom we know as Homo sapiens. They began their great exodus from the cradle of humanity, and the most powerful wave of this migration surged beyond the continent approximately 60,000 to 70,000 years ago. Their path lay north, and about 45,000 years ago they reached Europe, a land that had belonged to the Neanderthals for many millennia. Imagine this meeting of two worlds. Physically, our ancestors were strikingly different from native Europeans. They were taller, slimmer, their bones were not as massive, and their facial features were more refined. Their very anatomy, ideally suited for long journeys and efficient body cooling, marked them as newcomers from the sweltering heat of Africa. But it wasn't just their bodies. Their minds were wired differently, tailored for complex social relationships. The Cro-Magnons, the first representatives of our species in Europe, brought with them a veritable cultural revolution. They created what can be called the first tailored clothing to escape the brutal cold. Their brains, although no larger than those of Neanderthals, had a completely different internal structure. Scientists believe that it was this reorganization of neural connections that gave them more complex cognitive abilities, paving the way for evolutionary advances. The arrival of the Cro-Magnons in Europe marked the beginning of a new era, an era of incredible technological and cultural advances. They developed far more sophisticated hunting tools, including lightweight and deadly throwing spears, and then revolutionized the field with the invention of the bow and arrow. Their toolbox is astonishingly diverse: ultrafine blades, wood engraving tools, and specialized tools made of bone, antler, and mammoth tusks. These advanced technologies allowed them to hunt with unprecedented efficiency and exploit a much wider range of natural resources. These people had complex social structures, built extensive trade networks spanning hundreds of kilometers, and their symbolic thinking found expression in art, personal adornment, and elaborate funerary rituals. Consider their approach to resources. While Neanderthals typically made do with local stone, our ancestors were willing to travel vast distances to obtain high-quality flint from distant quarries. This suggests a completely different level of planning, organization, and perhaps even the beginnings of true trade. The period when Neanderthals and early modern humans lived side by side in the vast expanses of Europe for several thousand years remains one of the greatest mysteries of paleontology. The exact nature of their interactions is a subject of heated debate, but genetics provides an irrefutable answer. They interbred. This means that many of us, people of non-African descent, carry a small but significant trace of Neanderthal heritage in our DNA. The reasons why Neanderthals ultimately disappeared from the scene are multifaceted. It was likely a tragic combination of several factors: relentless climate change, fierce competition for resources with more technologically advanced aliens, and perhaps lower birth rates or vulnerability to new diseases. It was likely this deadly cocktail that led to their complete extinction. Yet, both Neanderthals and our direct ancestors demonstrated a remarkable ability to adapt to the harsh conditions of the Ice Age. They were skilled hunters and gatherers, able to build sturdy shelters and craft tools that helped them survive. Their very presence in these vast, ice-bound landscapes is a testament to incredible resilience and an invaluable window into our own past. Neanderthals roamed in small, mobile groups, following herds of wild animals and the seasonal ripening of edible plants. Their survival depended entirely on a profound understanding of their surroundings and the habits of animals. Stone Age people, tempered in the icy furnace, were true masters of their craft. They possessed secret knowledge about the properties of various materials and knew how to transform them into perfect tools. This knowledge was passed down orally, from father to son, ensuring the survival and prosperity of their culture in a world that demanded continuous innovation and an iron will to survive. The Ice Age became a severe test for all of humanity, a trial that forged the very physical and mental traits that make us human. Survival in that era was unthinkable without the ability to create and use tools. These tools, which we call Stone Age tools, weren't just rock fragments. No, they were complex technologies that evolved over hundreds of thousands of years. They allowed people to hunt, butcher prey, process hides, and create everything they needed to survive in that harsh and dangerous world. What materials did they choose? Just like today, ancient craftsmen favored what was readily available and possessed the required properties. The foundation of their techniques was stone, bone, antler, and wood. Stone was the king of materials. Ancient people were constantly searching for special types of stone, those that split predictably, creating cutting edges sharper than any steel. Flint and quartz were worth their weight in gold thanks to their fine-grained structure, which gave the craftsman complete control over the cutting process. And where it could be found, volcanic glass, obsidian, was used. Yes, it was more brittle, but its edges possessed truly incredible sharpness, making it indispensable for the most delicate work. The primary technique for working stone was called press retouching, or simply dressing. Imagine a craftsman striking a stone blank with a precise measured blow using another stone hammer or a softer antler hammer. A thin, sharp fragment, a flake, is chipped from the blank. In skilled hands, both the blank, core, and the chipped flake could become valuable tools. The earliest and perhaps most famous stone tool was the hand axe. These double-ended, teardrop-shaped tools were the all-purpose Swiss army knife of the Stone Age. They could be used to butcher enormous animals, dig up edible roots, or shape wood. They fit perfectly in the hand, becoming a deadly extension of it. Over time, hand axes became increasingly refined, acquiring a perfectly symmetrical shape and razor-sharp edges. As human thought evolved, the emphasis shifted from massive tools to lightweight, efficient flake tools. Now, sharp fragments chipped from the core became the primary product. This was a breakthrough in raw material conservation. Dozens of scalpel-sharp tools could now be crafted from a single piece of precious flint. Among them, scrapers occupied a special category. These were flakes with one or more rounded, blunted edges for comfortable grip, and a single, carefully sharpened working blade. Their main purpose was to process hides. They were used to scrape away residual meat and fat from the underside of the skin, preparing it for further processing. It was this process that transformed the rough hide into a soft, flexible material, which was then used to sew clothing, build shelters, and fashion durable containers. The ability to create warm and durable clothing was a matter of life and death in the icy hell of the Ice Age. Dozens of types of scrapers existed, each perfectly suited to its task. One of the greatest technological leaps of that era was the invention of flake technology. A flake is a special flake, at least twice as long as it is wide, with perfectly parallel edges. They were produced using highly complex processing methods, cleaving a series of identical blanks from a pre-prepared core. The flakes produced long, even, and incredibly sharp cutting edges, greatly increasing the efficiency of any work. These blanks could be used as butcher knives or transformed into other, even more specialized tools. Arrowheads were key to successful hunting. They were carefully crafted stone slabs, most often triangular or leaf-shaped, specifically designed to be attached to the shaft of a spear or dart. Early arrowheads were fairly simple, but over time, true masterpieces of engineering emerged, such as spear throwers or atlatls. This ingenious device acted as a lever, greatly increasing the range and killing power of a thrown spear. And at the end of the Ice Age, with the invention of the bow, Even miniature, finely crafted arrowheads appeared, allowing for precise and long-range hunting of the fastest game. But stone wasn't the only material. Ancient humans were virtuosos in using other materials as well. Animal bones and horns were invaluable resources, as they could be used to create strong and delicate tools that couldn't be made from brittle stone. Awls, sharp bone tools, were used to poke holes in hides for sewing. True needles, often made from bone or mammoth ivory with a tiny drilled eye, allowed for the creation of intricate, tailored clothing, crucial in cold climates. Harpoons with barbed tips for catching large fish were also carved from bone and horns. All these finds testify to our ancestors' profound understanding of the properties of a wide variety of materials. Although wood is almost completely absent from the archaeological record, it undoubtedly played a colossal role in their lives, serving as the material for shafts, handles, shelters, and much more. Imagine an Ice Age hunter. In his hands, not a stone, but something else, polished, light, yet deadly. A sharpened wooden spear may have been the very first weapon created by humans for obtaining food. But wood was not only for hunting, it was used to carve simple but effective sticks for digging up edible roots. It became the handles for heavy stone axes, making them much more convenient. Branches and trunks were used to construct frames for primitive shelters. But this versatile material had one huge drawback. It wasn't eternal. Time is merciless to wood, and so only meager fragments of what was once an entire world of wooden technologies have survived. And although wood was undoubtedly the foundation of life in the Stone Age, we know far less about it than about stone or bone, which have survived millennia. The journey through the Ice Age is not only a story of survival, but also a story of the mind, and this story is best told by the silent witnesses of the era: stone tools. Their evolution vividly demonstrates how the human brain became more complex, how its adaptability grew. It all began with crude, all-purpose hand axes. One tool for everything, butchering a carcass or digging up roots. But as hundreds of thousands of years passed, this simplicity gave way to brilliant specialization. Tools became increasingly elegant, deadly, and effective. Their creation required not just strength, but profound planning, skill, and an understanding of the properties of the material. We can trace this incredible journey, from the Acheulean hand axes, the workhorse of the ancient world, to the Mousterian flakes and side scrapers, and then to the pinnacle of Paleolithic technology, razor-thin blades and tiny but deadly microliths. It was a veritable technological arms race, with each new generation of craftsmen delving ever deeper into the secrets of stone. The ability to take an ordinary boulder and turn it into a sharp blade became the key to human dominance. These tools weren't just objects. They were extensions of the hand and mind, allowing our ancestors to survive and thrive in a harsh, unpredictable world. They gave us control over the elements, and they enabled us to take our place at the top of the Ice Age food chain. But perhaps the most astonishing thing the Ice Age people left us isn't their tools. It's a window into their souls. We're talking about cave art. Imagine, deep underground, in the impenetrable darkness of caves across Europe and beyond, lie incredible galleries of paintings, engravings, and sculptures. These aren't just drawings, they're a portal into the consciousness, the beliefs, the everyday drama of our distant ancestors. Looking at them, we see a level of artistic genius and symbolic thinking that continues to baffle scholars around the world. These masterpieces are not random sketches. They are complex, thoughtful compositions, often located in the most inaccessible, almost sacred corners of caves. This fact alone speaks to their importance to their creators. The most legendary temples of prehistoric art are found in Western Europe, primarily in what is now France and Spain. Here, we see such giants as the Lascaux and Chauvet caves in France and the famous Altamira in Spain. The Chauvet cave, which was revealed to the world only in 1994, contains some of the oldest works of art, created approximately 32,000–37,000 years ago. The Lascaux galleries, discovered in 1940, transport us back 17,000 years, captivating us with their vibrant colors. And the ceiling of Altamira, adorned with a herd of the famous bison, was painted approximately 14,000 years ago. All these and countless other monuments prove that art has lived in man for tens of thousands of years. What do we see on the walls of these ancient galleries? First and foremost, it's the animal world, the world that surrounded the ancient hunter. The Ice Age rock frescoes are a veritable bestiary of the megafauna that once ruled these lands. Mighty woolly mammoths, herds of European and steppe bison, galloping wild horses with lush manes, armored woolly rhinoceroses, graceful reindeer, and, of course, predators, ferocious cave lions and giant cave bears. The depictions of these animals are striking in their anatomical accuracy. Ancient artists possessed incredible powers of observation, but they didn't simply copy reality. They breathed life into the stone, conveying the movement, power, and energy of each animal. One of the most astonishing details is how the artists utilized the cave's relief. A natural bulge in the wall could represent the flank of a pregnant bison, and a crack in the stone could represent the leg of a running horse. This created a striking three-dimensional effect, as if the animals were about to step off the walls. But against this backdrop of animal splendor, people are almost completely absent. Human figures are extremely rare and, as a rule, are drawn very roughly, schematically. Sometimes we encounter downright strange creatures, half human, half beast, and alongside the realistic animals, we see mysterious abstract symbols, rows of dots, lines, grids, and other geometric patterns. Their meaning is one of the greatest mysteries of the past. Among the most frequent and personal motifs are human handprints, made like stencils. Ancient man pressed his hand to the wall and sprayed paint around it, leaving an eternal mark on the stone. How were these masterpieces created? The artist took everything he needed from nature. The paints were minerals ground into powder. Red, yellow, and brown hues came from ochre, a natural pigment based on iron oxide. Black was obtained from charcoal or manganese dioxide. For white, clay or chalk were sometimes used. This powder was mixed with a binder, animal fat, blood, or simply water, to create true paint. It was applied in a variety of ways. Sometimes the artist simply painted with his fingers or a clump of moss. Other times, brushes made from animal hair or bundles of plant fibers were used. But the most advanced technique was spraying. The artist would scoop powdered pigment into his mouth, hold a hollow bone or reed to the wall, and forcefully blow the paint out. The effect was similar to a modern airbrush, ideal for creating outlines or filling in large areas. Besides painting, engraving also existed. Images were simply scratched into the soft rock surface with a sharp flint biren. The scale of the work is staggering. In some caves, archaeologists have found the remains of wooden scaffolding or ladders. This means the artists worked at heights of several meters, right under the ceilings, which required enormous effort and complex planning. So why was all this necessary? What moved the hand of the ancient master, compelling him to descend into the icy darkness of the dungeons? There is no single answer to this question, and scholars still fiercely debate it. Most likely, art served several important functions. One of the most popular theories suggests a magical, ritualistic purpose. Perhaps, by drawing animals pierced by spears, hunters were trying to ensure good luck in real life. This is so-called sympathetic magic, the belief that an image directly influences the real object. According to another hypothesis, the caves were the site of initiation rites, where young men became adult hunters. The drawings served as visual aids, passing down invaluable knowledge about animal habits and hunting tactics from generation to generation. Some researchers see traces of shamanic practices in this art. The shaman, in a trance, traveled to the spirit world, and the animals on the walls are images of those same spirits or their visions. Other scholars believe it was a form of storytelling. ancient comics that recounted important events, myths, or the deeds of ancestors. The mysterious abstract symbols could have been maps, astronomical calendars, or totemic signs. Of course, the simplest explanation cannot be ruled out. It was art for art's sake, a way to beautify the world and express creative impulse. But the fact that these masterpieces are hidden in the darkest and most dangerous corners of caves speaks to their special, sacred significance. They were not intended for everyone. Regardless of its true purpose, rock art tells us an incredible amount about the people of that era. It demonstrates their astonishing powers of observation and profound knowledge of the animal world with which they lived side by side. For them, animals were more than just a source of food. They were central characters in their mythology, their universe. This art is irrefutable proof of our ancestors' capacity for abstract thought and the creation of complex symbolic systems. The sheer effort invested in creating these paintings, from the procurement and preparation of paints to the work in the dark by torchlight, testifies to a highly developed culture with a division of labor and shared spiritual goals. Cave art is a striking monument to the intellect and creative genius of our ancestors. It proves that even in the harshest conditions of the Ice Age, the human spirit sought a way to express itself, make sense of the world, and leave a mark that has not been erased by millennia. During that harsh era, both Neanderthals and our direct ancestors, early modern humans, organized their lives in settlements of various types. These ranged from tiny temporary hunting camps to much more substantial long-term encampments. Humans lived a nomadic life, often establishing camps that could last from a few days to several seasons, depending on animal migration, resource availability, and tribal traditions. These camps were the heart of their world, providing shelter, a place to craft tools, prepare food, and, just as importantly, a place to socialize. Understanding how our ancestors built their dwellings helps us appreciate their incredible resilience and ingenuity in the struggle for survival. The types of shelters depended heavily on the landscape and available materials. Where nature itself provided a ready-made home, in areas with cliffs and gorges, people naturally used caves and rock shelters. In this harsh prehistoric world, where nature itself was both ally and enemy, caves became true fortresses. Their stone vaults served as a reliable shield from the relentless elements, icy winds, torrential rains, and snowstorms. Inside these natural shelters, a remarkably even temperature was maintained. But our ancestors didn't simply occupy these spaces, they inhabited them. Imagine, inside the cave at the entrance, additional barriers were erected to protect against drafts, and in the depths, on special platforms, sleeping areas were arranged. Skins of killed animals, durable wood, and even massive bones were used. Excavations in ancient caves across Europe reveal a picture of a well-thought-out lifestyle. Archaeologists are finding traces of support pillars and the remains of hearths, not randomly placed, but in strategic locations. This suggests that the living space was clearly zoned and planned. Some of these cave dwellings served as shelters for people for many generations, sometimes even millennia. They became a kind of family nests, important centers for nomadic groups who moved across these ancient lands. But what to do where there were no sheltering cliffs? On the vast plains of Eastern Europe and Siberia, where the landscape was exposed to all winds, ancient people demonstrated incredible ingenuity. They learned to build complex and reliable temporary shelters, and their main building material was the remains of Ice Age giants, primarily the mighty mammoths. Let's travel to the Mezhyrich site in modern-day Ukraine. Here, we see striking structures, round or oval huts, the walls of which are constructed from dozens, sometimes hundreds, of mammoth bones, skulls, femurs, and pelvises, all skillfully fitted and fastened together, forming a strong, almost indestructible framework. This bone structure was most likely covered with thick skins of the same mammoths or reindeer, creating a warm and weather-resistant shelter. Just imagine the level of organization and collaborative effort required to assemble, transport, and erect such a monumental structure. Some of these houses were particularly large. Multiple fireplaces burned inside them, allowing for either dividing the space into sections or providing shelter for several families at once. And while these bone houses were not permanent, they served as reliable seasonal bases where one could live in relative comfort for weeks, even months. Of course, other materials were also used. Wood was undoubtedly a primary material, but it has almost completely disappeared. But even the meager finds paint a picture. At some sites, archaeologists have discovered traces arranged in a circle. These are all that remain of wooden posts dug into the ground. It can be assumed that they served as the foundations for shelters, which were then covered with skins or brush branches. And of course, such camps were always located near sources of life, water. Smaller bones, such as reindeer antlers, were also not wasted. They were always at hand and were used to make many useful, albeit less monumental, items. The life of ancient hunters was constantly on the move, and their shelters had to match this rhythm. They had to be quickly assembled and just as quickly dismantled. They were mobile homes that could be easily erected and rebuilt wherever needed. The entire life of these first human communities revolved around three main tasks: obtaining food, staying warm, and protecting themselves from predators. Their society likely already had a clear division of responsibilities. While some, the strongest and most resilient, went hunting, others gathered plant foods, prepared food, crafted tools, or maintained order in the camp. Imagine a group of hunters venturing deep into the wilderness for several days to track and hunt down a huge animal. A successful hunt was a true celebration for the entire tribe. The animal's carcass was butchered communally, and people could finally savor the taste of fresh, nutritious meat. For this task, they had specialized stone tools, ideal for effectively processing the carcass. Some meat was eaten immediately, fresh. The rest was dried or cured for future use, or rendered for its precious fat. Hides were meticulously processed, cleaned and tanned with scrapers, and perhaps even the animal's brain. They were then used to sew warm clothing, blankets, and coverings for their homes. Bones and antlers were transformed in the hands of skilled craftsmen into tools, deadly weapons, and even the first ornaments. But the heart of any camp, its pulsating center, was the fire. A hearth wasn't simply lit, it was carefully built and maintained. It provided warmth in the icy cold, light in the pitch-black night. Food was cooked on it, and its flames warded off the most dangerous predators. In large camps, traces of several hearths have been found. Each family likely gathered around their own fire, creating a sense of community while still maintaining privacy. Cooking over fire wasn't just a whim. It was a vital necessity. Heat treatment not only made food tastier, but also broke down tough fibers, making it more digestible and nutritious. Fire made food, especially meat, truly accessible to the human body. But it was also used for other purposes, for example, to harden wooden spearheads or to process other materials. How did these ancient people organize their social lives? We seek answers in archaeological finds and, drawing parallels, study modern hunter-gatherer tribes. Most likely, these groups were small, consisting of a few related families, perhaps 25 to 50 people. This size was ideal. It was sufficient for organizing collective hunts and fairly distributing resources, but it also did not deplete the surrounding territory too quickly. Important decisions were apparently made by the entire community or a council of respected elders, and sharing the spoils, especially after a large game hunt, was a crucial social glue that cemented bonds within the group and guaranteed everyone's survival. Community members who were unable to hunt, the sick, the wounded, or the elderly, were not abandoned to their fate. They were cared for. We have striking evidence that elderly or disabled members were given special attention. Let's recall the Neanderthal from the cave of La Chapelle-aux-Saints, who lived to a ripe old age despite suffering from severe ailments. This is only possible in a society with deep feelings of community and empathy. Ancient camps were more than just a place to spend the night, they were centers for the transmission of knowledge. It was here, among fellow tribesmen, that young people learned vital skills: how to craft the perfect stone tool, how to track game, how to read tracks in the ground, and how to understand animal habits. The stories, experiences, and observations shared around the nightly fire were invaluable. They were living textbooks, ensuring cultural continuity and the transmission of wisdom from one generation to the next. Discoveries of personal jewelry, beads and pendants, as well as magnificent rock paintings, tell us that this harsh life also found room for creativity, symbolic rituals, and the development of a complex cultural identity. These settlements were more than just shelters. They were vibrant social centers, where, in the icy breath of the era, the foundations of human civilization were born. During the Ice Age, our planet looked completely different. Imagine, enormous ice caps, several kilometers thick, encased the continents. These gigantic glaciers held colossal amounts of water, causing a sharp drop in sea levels. Then, vast tracts of land, continental shelves, usually hidden underwater, emerged from the depths. These suddenly emerging lands became natural bridges, connecting continents that are now separated by seas and oceans. These land bridges became crucial corridors through which animals, plants, and, most importantly, ancient human populations were able to overcome enormous geographic barriers. The most famous and grandiose of these bridges was Beringia. This vast landmass connected Northeast Asia, or Siberia, with northwestern North America, or Alaska. Today, the Bering Strait separates these two continents, but at the height of the last ice age, approximately 20,000 to 26,000 years ago, sea levels dropped to their lowest point. Beringia then became a vast ice-free landmass. At its widest point, it could reach 1,500 kilometers. This wasn't just a narrow isthmus, but an entire subcontinent with its own unique ecosystems. Due to its geographic location, the ice sheets sucked all the moisture out of the atmosphere, so Beringia itself remained virtually ice-free, covered in cold but nutritious grasses. This tundra-like environment provided food for countless herds of large animals, including woolly mammoths, steppe bison, wild horses, and reindeer. Beringia served as a vital migration corridor for these species to move between Asia and North America. Animals that evolved in Eurasia were able to penetrate the New World and vice versa. This great exchange enriched the biodiversity of both continents and facilitated the emergence of new species perfectly adapted to harsh conditions. For example, the ancestors of modern American bison, horses, and even camels originated in Asia and crossed Beringia into North America. At the same time, some North American species, albeit in smaller numbers, made the journey westward to Asia. But Beringia wasn't the only such bridge. Other land corridors also played a colossal role in shaping the map of life on the planet. Between mainland Australia and New Guinea, the Sahel Shelf became exposed during periods of low sea levels, forming a single landmass. This bridge became the key to unlocking the early human colonization of Australia, allowing the first humans to migrate from Southeast Asia. A similar story unfolded with Sunderland, a land bridge that connected mainland Southeast Asia with the islands of Sumatra, Borneo, and Java. During ice ages, it remained dry land, facilitating the movement of animals and ancient human populations across territories that are now island nations. It was these connections that allowed early Homo sapiens to disperse across the islands of Southeast Asia and reach Oceania. Another striking example is the land connection that existed between modern-day Great Britain and mainland Europe. Let's travel back in time to a time when the world map itself looked completely different. During the height of the Great Ice Ages, gigantic ice caps encased the planet, and sea levels were much lower than they are today. This retreating water exposed vast tracts of land, creating natural bridges between continents that are now separated by seas. Thus, a colossal land corridor emerged between Asia and North America, known as the Bering Land Bridge. a veritable gateway to a new, unexplored world. Now let's look at Europe. Where the cold waters of the North Sea lap today, during the same ice age, there was a vast grassy lowland that scientists have named Doggerland. It was not just an isthmus, but an entire lost world, directly connecting the British Isles with the European mainland. Herds of ancient animals roamed these lands, and in their wake, groups of early humans followed in their footsteps. But time is inexorable. As the glaciers began their great retreat, meltwater rushed back into the oceans. Sea levels rose steadily, engulfing Doggerland, until finally, the turbulent waters formed the English Channel, isolating Britain forever. How did this grand mechanism, creating and destroying entire terrestrial worlds, work? It all lies in the great cycles of glaciation, the very breath of the planet. Imagine gigantic ice sheets, kilometers thick, accumulating at the poles. This ice is nothing more than frozen water extracted from the world's oceans. The larger the glaciers grew, the more water they absorbed, and sea levels across the planet inexorably fell. And when warming set in, the glaciers melted and trillions of tons of water returned to the ocean, flooding lowlands and once again severing land connections. This process repeated itself over and over again, meaning these corridors between worlds did not exist forever. They appeared and disappeared with the rhythm of ice ages. The peak of this phenomenon occurred during the last glacial maximum. At that time, the world's oceans were a staggering 100 to 120 meters below their current levels. Just imagine the scale of this. Vast tracts of continental shelves, now hidden underwater, became dry land, creating numerous land bridges across the globe. These ancient routes were of colossal, fateful significance for human history. And central to this drama is, of course, Beringia, the bridge between Asia and America. It was along this bridge, according to the leading theory, that our ancestors first set foot on the New World. This was a great migration that brought people, their culture, and their technologies to an entirely new virgin continent. Moving along these land corridors, ancient hunter-gatherer tribes weren't seeking to conquer the world. They were simply following their prey. Vast herds of animals migrated in search of pasture, and people followed them, for their survival depended on it. This is precisely what fueled the dispersal of our species across the planet. The emergence and disappearance of these bridges directly influenced how peoples dispersed, how their cultures developed, and how genetic diversity developed across the continents. These dynamic corridors were the arteries of the ancient world, through which life itself flowed. The mystery of the original peopling of the Americas still captivates scientists. It's one of the greatest detective stories in paleontology. According to the leading theory, the first modern humans made an incredible journey from Asia to North America, using the very same Bering Land Bridge. It was a monumental journey undertaken by daring hunters during a time when the world was frozen solid. As a result of this voyage, humans populated two vast continents, from the icy wastes of the Arctic to the southernmost reaches of Patagonia. Their journey began in the harsh lands of Northeast Asia, most likely in what is now Siberia. The tribes there were perfectly adapted to life in the brutal cold. During the peak of the last glaciation, approximately 20,000 to 26,000 years ago, a global drop in sea levels opened a path for them, a gigantic land bridge, Beringia, connecting Siberia and Alaska. This land, contrary to expectations, was not covered in ice. Instead, it was a cold but rich steppe, ideal grazing ground for mammoths, bison, and wild horses. And where there is prey, there are hunters. It is believed that the first groups of people moved slowly, generation after generation, eastward, following migrating herds. They crossed Beringia and ended up in what is now Alaska. It's important to understand this wasn't a rapid march. Rather, it was a long process, spanning thousands of years. People may have lived in Beringia itself for millennia before moving further into the American interior. But when exactly did they make this decisive step south? This question is the subject of fierce debate. For decades, the prevailing theory was that the first true Americans were members of the so-called Clovis culture. Their distinctive, skillfully crafted stone spearheads were found across the continent, and it seemed that the history of the settlement of America began with them, approximately 13,500 years ago. However, as often happens in science, new discoveries turned everything upside down. Archaeologists began unearthing evidence that was much, much older. It was like an earthquake in the scientific world. Sites like Monteverde in Chile, estimated to be at least 14,500 years old, or Paisley Caves in Oregon, with similarly ancient human footprints, provided irrefutable proof. Humans were in the Americas long before the Clovis culture. This means they arrived here before the land corridor to the south opened, and perhaps even before ice-free passage opened between the glaciers. Picture this. Upon arriving in Alaska, the first settlers found themselves trapped. Their route south was blocked by two enormous ice sheets, the Laurentide ice sheet in the east and the Cordilleran ice sheet in the west. These icy mountains, covering much of modern-day Canada, seemed an impassable wall. It was long believed that people were forced to wait thousands of years for a corridor between these two ice sheets to melt, allowing passage. Such a passage did indeed appear, but only about 14,000 years ago. But how then to explain the much older finds in Chile and Oregon? This led scientists to consider another alternative route. This is how the coastal migration hypothesis was born. According to it, the first humans didn't wait for an ice corridor to open, but moved south along the Pacific coast, possibly on primitive boats or rafts. They moved from one ice-free area to another, subsisting on the abundant seafood, fish, shellfish, and seaweed. This route was open to them even when the interior of the continent was frozen solid. But whatever route they took, one thing is certain. Once humans emerged from the ice sheets, their spread across the Americas was astonishingly rapid. Within just a few thousand years, their traces can be found across vast distances. These ancient Americans were incredibly skilled and resilient hunter-gatherers, capable of adapting to any conditions. They hunted gigantic megafauna, wool mammoths, mastodons, giant sloths, and saber-toothed cats, masterfully using their stone tools. Their diet was supplemented by fish, birds, and a variety of plants. Spreading across North America, from the Great Plains to the eastern forests, they created new cultures and adapted to diverse ecosystems. Their expansion into South America was even more rapid. In just 2,000 years, they reached the southernmost reaches of the continent, the frigid lands of Patagonia. This speed speaks to their incredible mobility and profound knowledge of the world around them. Of course, this journey was no walk in the park. The first Americans encountered unfamiliar landscapes, new predators, and a constantly changing climate. But their ingenuity, unity, and technological skills enabled them to achieve the impossible, colonizing two vast, previously uninhabited continents. Modern genetics fully confirms this picture. Native American DNA unmistakably points to their Asian ancestors. Moreover, genetic diversity decreases from north to south, clearly charting the route of their great expansion. The story of the peopling of the Americas is a gripping saga of exploration, survival, and the indomitable human spirit that drives us to discover new worlds and forever change the face of the planet. At the same time, during the last glacial maximum, which reigned over the Earth from 110,000 to 12,000 years ago, Europe presented a completely different spectacle. Its appearance was defined by gigantic ice sheets and bone-chilling cold. This period, known as the Upper Paleolithic, was a time of severe trials and great achievements for our European ancestors. Imagine Europe, but not as we know it today. Fast forward tens of thousands of years into the past, to an era when the continent became the stage for a grand drama of survival played out by two different species of people. Here, amid the ice and frigid steppes, flourished the cultures of both the Neanderthals, the original inhabitants of this harsh world, and the newcomers, our direct ancestors, the early modern humans. Both species demonstrated an incredible ability to adapt to the harshest conditions. This world was a living, breathing organism, where giant glaciers sometimes advanced, sometimes retreated, shaping the landscape and dictating the rules of life for all who dared to inhabit it. At the very peak of this ice age, during an era scientists call the last glacial maximum, approximately 20,000 to 26,000 years ago, the colossal Scandinavian ice sheet rose above northern Europe. This icy monster originated in the mountains of Scandinavia and began its slow, inexorable march south. It crept across the Baltic Sea, burying the entire territory of today's Norway, Sweden, and Finland. Its icy fingers reached as far as Denmark, Germany, Poland, and Russia. It covered virtually the entire British Isles, leaving only a few isolated mountain peaks in the south, like the last islands in a frozen ocean. At its center, this ice mass was several kilometers thick, and its weight was so enormous that it literally pressed into the Earth's crust, leaving deep scars that we know today as the majestic Norwegian fjords and the thousands of lakes of Finland. South of this colossal ice wall lay lands uncovered by ice, yet still subject to its icy grip. Much of Western and Central Europe was periglacial, meaning the land was locked in permafrost, frozen to enormous depths. Instead of dense forests, there was vast, treeless tundra and frigid steppes. The landscape was alien, dotted with strange patterns on the ground and icy hills known as pingos, all the result of endless cycles of freezing and thawing. Further south, around the Mediterranean, the climate was much cooler and drier than it is today, and although the giant continental glacier hadn't reached here, high mountain ranges like the Alps and Pyrenees gave birth to their own mighty valley glaciers, flowing down into the valleys. These global climate changes completely redrew the vegetation map. Forests, fleeing the cold, retreated to small refuges in the southernmost reaches of Europe, giving way to the vast grasslands that covered glacial Europe. These vast meadows and tundra became home to countless herds of gigantic animals. The people who lived in these inhumane conditions were true masters of survival. The first to emerge were the Neanderthals, a species that evolved in Europe over hundreds of thousands of years and was perfectly adapted to this world. Their powerful, stocky build, with short limbs and a broad chest, was a true evolutionary marvel, designed to conserve heat in the frigid climate. Neanderthals were fearless and skilled hunters. Armed with heavy spears, they engaged in deadly battles with the largest animals of the era: woolly mammoths, woolly rhinoceroses, giant bison, and wild horses. It was a head-to-head hunt, requiring incredible strength and courage. Archaeological finds, such as those at the La Chapelle-aux-Saints site in France, tell a remarkable story. Neanderthals cared for their elderly and sick, suggesting a complex social structure and compassion. Their stone-working technology, known as the Mousterian culture, was extremely efficient and allowed them to create tools for a wide range of tasks, from butchering carcasses to processing hides. They most often chose natural caves and rock overhangs as their homes, providing reliable shelter from the merciless winds and freezing temperatures. But approximately 45,000 years ago, new players entered this icy scene. Early modern humans, our ancestors of the species Homo sapiens, arrived in Europe after a long journey from Africa and the Middle East. Their arrival marked the beginning of a new era, the Upper Paleolithic, a time of incredible technological and cultural advances. These people, often referred to as Cro-Magnons, brought with them an entirely new, far more sophisticated toolkit. They masterfully crafted thin, sharp stone blades and sophisticated tools from bone, antler, and mammoth tusks. Their arsenal included specialized spearheads that could be thrown from long distances, bone needles for sewing, and even engraving tools. This ability to create unique objects laid the foundation for the emergence of art and self-expression. And clothing, sewn from animal skins using those very same bone needles, was a true revolution. It provided incomparably better protection from the cold than simple capes, and gave man the key to survival in the heart of the Ice Age. Early modern humans were a completely new breed of hunter. They relied not only on brute strength, but also on intelligence, developing complex strategies. they organized communal drives, driving herds of animals into traps and ambushes, and developed projectile weapons that allowed them to strike prey from a safe distance. Their diet was far more varied. They hunted not only giant beasts, but also small animals, fish, and birds, demonstrating remarkable flexibility and an ability to utilize all available resources. Their settlements could be found both in caves and in open spaces. There, they built amazing dwellings, sometimes using enormous mammoth bones as frames. True masterpieces of prehistoric architecture have been found, for example, at the Megerik site in Ukraine. But the main breakthrough occurred in the world of spirit and symbols. The Upper Paleolithic era was a time of veritable creativity. We see this in the stunning cave art preserved in the caves of Lascaux and Chauvet in France and Altamira in Spain. On the walls of these deep underground chambers, by the flickering flames of torches, ancient artists depicted animals with incredible realism and dynamism. Created with mineral paints, these drawings, according to scholars, were not simply decorative, but had profound ritual, magical, and even educational meaning. In addition to cave paintings, these people created countless small works of art that we can handle. These include carved animal figures, the famous Venus statues, and all kinds of beads and pendants, which indicate the emergence of personal adornment and complex symbolic thinking. They also practiced complex burial rituals, burying their dead with grave goods, which may indicate a belief in the afterlife and a special attitude towards the deceased. The history of the coexistence of Neanderthals and early modern humans in Europe for several thousand years remains full of mysteries. Genetic studies show that these two species not only coexisted, but also interbred. However, around 40,000 years ago, Neanderthals disappeared forever. The causes of this tragedy are likely rooted in a complex set of factors. Sharp climate fluctuations, increasing competition from the more numerous and technologically advanced Homo sapiens, and possibly differences in adaptability or reproductive rates. Even at the very end of the Ice Age, nature delivered a final, cruel surprise, a sharp cold snap known as the Younger Dryas. And yet, despite all these challenges, the human cultures of Ice Age Europe demonstrated incredible resilience, ingenuity, and artistic genius, laying the foundation for all subsequent human development. Now let's shift our gaze east to the planet's largest continent, Asia. Here, the Ice Age played out a completely different scenario. From the gigantic ice fields of Siberia to the subtle climate shifts in the southern regions, Asia was a world of contrasts. When the Ice Age ended around 12,000 years ago, much of northern Asia was a realm of bitter cold, permafrost, and endless steppes. This vast landmass became a key arena for the evolution and migration of ancient human populations, including those brave souls who eventually became the ancestors of Native Americans. Northern Asia, and Siberia in particular, was located in a periglacial zone. Although it lacked a continuous ice cap like Europe or North America, vast areas were frozen solid. Mountain ranges such as the Himalayas, Altai, and the Tibetan Plateau contained massive glaciers and ice caps. The northern plains of Siberia hosted a unique and incredibly rich ecosystem, the so-called Mammoth Steppe. This vast, cold grassland stretched from Eastern Europe across Siberia all the way to Mongolia. It was home to countless herds of Ice Age megafauna, woolly mammoths, woolly rhinoceroses, steppe bison, and wild horses. These animals provided an inexhaustible source of food and materials for ancient hunters. The climate across much of North and Central Asia was extremely cold and dry. Fierce winds reigned supreme across the treeless plains. They picked up dust from glaciers and carried it for thousands of kilometers, creating enormous deposits of fertile soil known as loess, particularly in parts of China that are still renowned for their fertility today. At the same time, aridity led to the expansion of deserts in some regions of Central Asia. Further south, in Southeast Asia, there was no direct glaciation, but the climate cooled and sea levels dropped by tens of meters. This exposed vast tracts of seafloor, creating a gigantic land bridge known as Sunderland, connecting mainland Asia with the modern islands of Sumatra, Borneo, and Java. This opened the way for the migration of animals and people. A similar process occurred further south, where the Sahul Shelf connected Australia and New Guinea, playing a key role in the settlement of the Australian continent. The human presence in Asia during the Ice Age is an incredibly important and multifaceted story. It was here that key events in the global dispersal of humanity unfolded. The first modern humans, Homo sapiens, left Africa and arrived in Asia in several waves, beginning approximately 60,000 to 70,000 years ago. From here, they began their triumphant march across the planet, gradually spreading across the vast continent and adapting to a wide range of climates, from the icy steppes of the north to the tropical forests of the south. Fossil finds and archaeological excavations in East Asia confirm this great story of the exploration of a new world. Let us travel to the icy world of the distant past, to the very heart of Siberia, approximately 30,000 years ago. Here, beyond the Arctic Circle, where permafrost reigns today, life was already thriving. Small bands of courageous hunters braved the elements, proving that human willpower can conquer even the most brutal cold. Imagine a discovery made near the banks of the Yana River, the horn of a mighty woolly rhinoceros, crafted by ancient human hands. This is more than just an artifact. It's proof of incredible adaptation. These people were masters of survival. They led deadly hunts for Ice Age giants, developing unique strategies and crafting specialized tools to secure sustenance in this harsh, frozen world. But Ice Age Asia became the stage for a far more monumental event, one that forever changed the map of humanity, the settlement of the American continents. As we already know, at that time, a gigantic land bridge known as Beringia existed, connecting northeastern Asia with Alaska. And so, forged in the icy crucible of the Siberian steppes, human populations began their great journey. They didn't travel blindly. They followed migrating herds of mammoths, bison, and reindeer. It was an epic migration, stretching for millennia. Some groups lived in the vastness of Beringia itself for so long that it became their true homeland, before they ventured further south, exploring the uncharted lands of North and then South America. And this great story of migration, as if carved in the ice of time, finds its irrefutable confirmation in the genetic code of modern Native Americans, whose roots are firmly linked to the ancient population of East Asia. Across the vast expanse of Asia, a mosaic of unique human cultures flourished. Each group developed technologies ideally suited to their particular environment. On the vast steppes, nomadic hunter-gatherers honed their skills in pursuing large game. Their arsenal included spear throwers, and, over time, bows and arrows emerged. Their stone tools, sharp blades, points, and scrapers, were perfect for butchering carcasses and processing tough hides. A completely different picture emerged in forested or coastal regions. Here, the bounty of the sea and forests formed a completely different diet, and, accordingly, required different tools. But wherever these people lived, we find evidence of their complex social organization, ritual practices, and commitment to symbolism. Throughout Asia, archaeologists are discovering the first glimmers of art and self-expression, delicate beads carved from seashells or animal bones. But the Ice Age couldn't last forever. The world began to thaw. Global warming brought with it colossal changes. The gigantic ice sheets that had encased the continents began to melt, turning into mighty rivers and raising sea levels. This great flood inundated land bridges like Sunderland and Beringia, forever changing coastlines and turning peninsulas into islands. The vast mammoth steppe, which had supported countless herds of giants, began to disappear, giving way to dense forests and new types of grasslands. For many of the great animals of the Ice Age, this was a death sentence. Their world was disappearing, and they were disappearing with it. Human populations faced with these monumental changes once again demonstrated their incredible capacity for adaptation. They shifted their strategies, exploited new resources, and it was these changes that ultimately led to the greatest revolution in human history, the emergence of agriculture. Thus, in the fertile lands of Western Asia and the river valleys of the East, the foundations of the future agrarian world were laid. The Ice Age in Asia was more than just an era of cold. It was a time of great trials that spurred humanity to incredible cultural innovations, adaptations, and monumental migrations that shaped the face of our entire world. When we hear the word Ice Age, our imagination conjures up images of endless ice sheets and woolly mammoths trudging through the snow. However, it's important to understand that Africa, the cradle of humanity, located primarily in the tropics, lived by its own rules. There were no gigantic continental glaciers here. And yet, the last ice age, which raged across the planet from approximately 110,000 to 12,000 years ago, had a profound impact on the climate, ecosystems, and the very fate of the African continent. The history of Africa during this era is a unique saga of adaptation to change and a key act in the drama of modern human evolution and dispersal across the planet. Glaciation here was localized. Only on the highest mountain ranges did glaciers rest, like ice crowns. The peaks of mountains such as Kilimanjaro, Kenya, and Rwenzori in East Africa, as well as the Atlas Mountains in the north, were covered in ice caps. During the coldest phases of the Ice Age, these glaciers were significantly larger than today, but they remained isolated pockets of cold, not merging into a single ice sheet like those covering Europe and North America. But the absence of ice did not mean stability. Africa was experiencing massive and dramatic climate shifts. The main trend was the onset of aridity. The shadow of a great drought, which reached its peak approximately 20,000 to 26,000 years ago, deepened over the continent. Global cooling led to less evaporation from the oceans, meaning less moisture in the atmosphere. Rainfall over much of Africa became rare. The continent began to dry out. The great deserts of the Sahara and Kalahari expanded, turning into even more lifeless and harsh spaces. They became insurmountable barriers, separating animal and human populations. Even the mighty tropical forests of Central and West Africa succumbed to the onslaught of drought. They shrank, disintegrating into small, isolated pockets of life, a kind of refuge where species could wait out unfavorable times. This separation of ecosystems led to the fragmentation of all life, creating periods of isolation followed by moments of renewed contact. The decline in precipitation dealt a devastating blow to the continent's waterways. Water levels in giant lakes like Victoria dropped catastrophically, while many smaller lakes and swamps simply disappeared, leaving behind only salt crusts. Mighty river systems, including the Nile, dried up, their flows altered. This hydrological stress became a true test for all living things, forcing plants, animals, and people to either adapt to the new, harsh conditions or migrate in search of salvage moisture. Of course, there were brief periods when some regions became slightly wetter, but the overall picture of the glacial maximum in Africa was cold and, most importantly, extremely dry. Strong winds blowing from the glacial margins only exacerbated the situation, raising clouds of dust and further desiccating the land. These climate swings had a dramatic impact on Africa's flora and fauna. Where forests retreated, savannas and grasslands expanded. This became a golden age for animals adapted to open spaces. Vast herds of wildebeest, zebras, and other herbivores thrived on these new grasslands. At the same time, forest species were pushed to the brink of extinction, losing their home. African megafauna, elephants, rhinos, and hippos, though they didn't need the woolly coats of their northern relatives, also suffered from the changes. Their survival depended directly on access to water and lush vegetation, both of which were becoming increasingly scarce. It was in these harsh conditions, in this crucible of climatic testing, that the character of a new species, Homo sapiens, was forged. Our ancestors evolved in Africa and adapted to its capricious climate long before they set out to conquer the world. Periods of drought and habitat fragmentation may have played a key role in our evolution. The formation of small, isolated groups of people may have facilitated the development of local adaptations and increased genetic diversity. And when the climate became more favorable, these groups expanded their territories, met, and exchanged not only genes, but also cultural achievements. The great exodus from Africa, which ultimately led to the dispersal of our species across the planet, was directly linked to these climate cycles. During periods of wetter climates, so-called green corridors appeared in the deserts. Like oases of hope, they allowed people to cross lifeless expanses, moving from Africa to the Middle East and further into Asia. These routes ran along coastlines or river valleys, where water and food could be found. The exact routes and timing of these migrations are still the subject of scientific debate, but one thing is clear: they would not have been possible without these brief climatic windows. Meanwhile, in Africa itself, humans were achieving incredible technological advances. They created sophisticated stone tools, skillfully crafted points, scrapers, and blades as part of the so-called Middle Stone Age industry. They didn't just survive, they thrived, developing diverse strategies for living in savannas, forests, and coastal areas. Their diet included shellfish, fish, a wide variety of plants, and, of course, the meat of land animals they successfully hunted. But most striking is the evidence of their complex symbolic thinking. Discoveries of personal ornaments, such as ostrich eggshell beads and early forms of rock art, reveal highly developed cognitive abilities and a nascent culture. Thus, the Ice Age in Africa became not just a backdrop, but an active driver of human evolution and culture.